Preface and Prologue of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam. Calculus Made Easy by Silvanus P. Thompson. What one fool can do, another can. Ancient Simian proverb. Preface to the second edition. The surprising success of this work has led the author to add a considerable number of worked examples and exercises. Advantage has also been taken to enlarge certain parts where experience has shown that further explanations would be useful. The author acknowledges with gratitude many valuable suggestions and letters received from teachers, students, and critics. October 1914. Prologue. Considering how many fools can calculate, it is surprising that it should be thought either a difficult or a tedious task for any other fool to learn how to master the same tricks. Some calculus tricks are quite easy. Some are enormously difficult. The fools who write the textbooks of advanced mathematics, and they are mostly clever fools, seldom take the trouble to show you how easy the easy calculations are. On the contrary, they seem to desire to impress you with their tremendous cleverness by going about it in the most difficult way. Being myself a remarkably stupid fellow, I have had to unteach myself the difficulties, and now beg to present to my fellow fools the parts that are not hard. Master these thoroughly, and the rest will follow. What one fool can do, another can. End of Preface and Prologue. Section 1 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam. Calculus Made Easy by Silvanus P. Thompson. Chapter 1. To deliver you from the preliminary terrors. The preliminary terror which chokes off most fifth-form boys from even attempting to learn how to calculate can be abolished once for all by simply stating what is the meaning, in common-sense terms, of the two principal symbols that are used in calculating. These dreadful symbols are 1. D, which merely means a little bit of. Thus, dx means a little bit of x, or du means a little bit of u. Ordinary mathematicians think it more polite to say an element of instead of a little bit of, just as you please, but you will find that all these little bits, or elements, may be considered to be indefinitely small. 2. The integral symbol, which is merely a long s and may be called, if you like, the sum of. Thus, the integral of dx means the sum of all the little bits of x, or the integral of dt means the sum of all the little bits of t. Ordinary mathematicians call this symbol the integral of. Now, any fool can see that if x is considered to be made up of a lot of little bits, each of which is called dx, if you add them all up together, you get the sum of all the dx's, which is the same thing as the whole of x. The word integral simply means the whole. If you think of the duration of time for 1 hour, you may, if you like, think of it as cut up into 3,600 little bits called seconds. The whole of the 3,600 little bits added up together make 1 hour. When you see an expression that begins with this terrifying symbol, you will henceforth know that it is put there merely to give you instructions that you are now to perform the operation, if you can, of totaling up all the little bits that are indicated by the symbols that follow. That's all. End of Section 1.
Section 2 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. On Different Degrees of Smallness. We shall find that in our process of calculation we have to deal with small quantities of various degrees of smallness. We shall have also to learn under what circumstances we may consider small quantities to be so minute that we may omit them from consideration. Everything depends upon relative minuteness. Before we fix any rules, let us think of some familiar cases. There are 60 minutes in the hour, 24 hours in the day, 7 days in the week, and there are therefore 1,440 minutes in the day and 10,080 minutes in the week. Obviously, 1 minute is a very small quantity of time compared with a whole week. Indeed, our forefathers considered it small as compared with an hour, and called it 1 minute, meaning a minute fraction, namely 1/60th of an hour. When they came to require still smaller subdivisions of time, they divided each minute into 60 still smaller parts, which in Queen Elizabeth's days they called second minutes, i.e., small quantities of the second order of minuteness. And nowadays we call these small quantities of the second order of smallness seconds, but few people know why they are so called. Now, if 1 minute is so small as compared with a whole day, how much smaller by comparison is 1 second? Again, think of a farthing as compared with a sovereign. It is barely worth more than 1/1000th part. A farthing, more or less, is of precious little importance compared with a sovereign. It may certainly be regarded as a small quantity. But compare a farthing with 1,000 pounds. Relatively to this greater sum, the farthing is of no more importance than 1/1000th of a farthing would be to a sovereign. Even a golden sovereign is relatively a negligible quantity in the wealth of a millionaire. Now, if we fix upon any numerical fraction as constituting the proportion for which any purpose we call relatively small, we can easily state other fractions of a higher degree of smallness. Thus, if, for the purpose of time, 1/60 be called a small fraction, then 1/60 of 1/60, being a small fraction of a small fraction, may be regarded as a small quantity of the second order of smallness. Footnote: the mathematicians talk about the second order of magnitude, i.e., greatness, when they really mean second order of smallness. This is very confusing to beginners. Or if for any purpose we were to take 1%, i.e., 1/100, as a small fraction, then 1% of 1%, i.e., 1/10,000, would be a small fraction of the second order of smallness, and 1/1,000,000 would be a small fraction of the third order of smallness, being 1% of 1% of 1%. Lastly, suppose that for some very precise purpose we should regard 1/1,000,000 as small. Thus, if a first-rate chronometer is not to lose or gain more than half a minute in a year, it must keep time with an accuracy of 1 part in 1,051,200. Now, if for such a purpose we regard 1/1,000,000 or 1/1,000,000th as a small quantity, then 1/1,000,000 of 1/1,000,000, that is 1/1,000,000,000 or 1/1000th, will be a small quantity of the second order of smallness, and may be utterly disregarded by comparison. Then we see that the smaller a small quantity itself is, the more negligible does the corresponding small quantity of the second order become. Hence we know that in all cases we are justified in neglecting the small quantities of the second or third or higher orders, if only we take the small quantity of the first order small enough in itself. But it must be remembered that small quantities, if they occur in our expressions as factors multiplied by some other factor, may become important if the other factor is itself large. Even a farthing becomes important if only it is multiplied by a few hundred. Now, in the calculus we write dx for a little bit of x. These things, such as dx and du and dy, are called differentials. The differential of x or of u or of y, as the case may be. You read them as dx or du or dy. If dx be a small bit of x, and relatively small of itself, it does not follow that such quantities as x times dx, or x squared dx, or a to the x power dx are negligible. But dx times dx would be negligible, being a small quantity of the second order. A very simple example will serve as illustration. Let us think of x as a quantity that can grow by a small amount so as to become x plus dx, where dx is the small increment added by growth. The square of this is x squared plus 2x times dx plus parentheses dx close parentheses squared. The second term is not negligible because it is a first order quantity, while the third term is of the second order of smallness, being a bit of x squared. Thus, if we took dx to mean numerically, say, 1/60 of x, then the second term would be 2/60 of x squared, whereas the third term would be 1/3600 of x squared. This last term is clearly less important than the second. But if we go further and take dx to mean only 1/1000 of x, then the second term will be 2/1000 of x squared, while the third term will be only 1/1,000,000 of x squared. Geometrically, this may be depicted as follows. Draw a square, the side of which we will take to represent x. Now suppose the square to grow by having a bit dx added to its size each way. The enlarged square is made up of the original square, x squared. The two rectangles at the top and on the right, each of which is of area x times dx, or together 2x times dx, and the little square at the top right-hand corner, which is parentheses dx close parentheses squared. In figure 2 we have taken dx as quite a big fraction of x, about 1/5. But suppose we had taken it only 1/100, about the thickness of an inked line drawn with a fine pen. Then the little corner square will have an area of only 1/10,000 of x squared, and be practically invisible. Clearly, parentheses dx close parentheses squared is negligible, if only we consider the increment dx to be itself small enough. Let us consider a simile. Suppose a millionaire were to say to his secretary, "Next week I will give you a small fraction of any money that comes in to me." Suppose that the secretary were to say to his boy, "I will give you a small fraction of what I get." Suppose the fraction in each case to be 1/100 part. Now, if Mr. Millionaire received during the next week £1,000, the secretary would receive £10, and the boy 2 shillings. £10 would be a small quantity compared with £1,000, but 2 shillings is a small quantity indeed, of a very secondary order. But what would be the disproportion if the fraction, instead of being 1/100, had been settled at 1/1000 part? Then, while Mr. Millionaire got his £1,000, Mr. Secretary would get only £1, and the boy less than 1 farthing. The witty Dean Swift once wrote, "So naturalists observe, a flea hath smaller fleas that on him prey, and these have smaller fleas to bite 'em, and so proceed ad infinitum." On Poetry, a Rhapsody, page 20, printed 1733, usually misquoted. An ox might worry about a flea of ordinary size, a small creature of the first order of smallness, but he would probably not trouble himself about a flea's flea, being of the second order of smallness. It would be negligible. Even a gross of flea's fleas would not be of much account to the ox. End of section 2.
Section 3 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. On relative growings. All through the calculus, we are dealing with quantities that are growing, and with rates of growth. We classify all quantities into 2 classes, constants and variables. Those which we regard as a fixed value, and call constants, we generally denote algebraically by letters from the beginning of the alphabet, such as A, B, or C, while those which we consider as capable of growing, or, as mathematicians say, of varying, we denote by letters from the end of the alphabet, such as X, Y, Z, U, V, W, or sometimes T. Moreover, we are usually dealing with more than one variable at once, and thinking of the way in which one variable depends on the other. For instance, we think of the way in which the height reached by a projectile depends on the time of attaining that height. Or we are asked to consider a rectangle of given area, and to inquire how any increase in the length of it will compel a corresponding decrease in the breadth of it. Or we think of the way in which any variation in the slope of a ladder will cause the height that it reaches to vary. Suppose we have got 2 such variables that depend one on the other. An alteration in one will bring about an alteration in the other because of this dependence. Let us call one of the variables x and the other that depends on it y. Suppose we make x to vary. That is to say, we either alter it or imagine it to be altered, by adding to it a bit which we call dx. We are thus causing x to become x plus dx. Then, because x has been altered, y will have altered also, and will have become y plus dy. Here, the bit dy may be in some cases positive, in others negative, and it won't, except by a miracle, be the same size as dx. Take 2 examples. 1. Let x and y be respectively the base and the height of a right-angled triangle, Fig. 4, of which the slope of the other side is fixed at 30 degrees. If we suppose this triangle to expand, and yet keep its angles the same as at first, then, when the base grows so as to become x plus dx, the height becomes y plus dy. Here, increasing x results in an increase of y. The little triangle, the height of which is dy, and the base of which is dx, is similar to the original triangle, and it is obvious that the value of the ratio dy over dx is the same as that of the ratio y over x. As the angle is 30 degrees, it will be seen that here dy over dx equals 1 over 1.73. 2. Let x represent, in Figure 5, the horizontal distance from a wall, of the bottom end of a ladder, AB, of fixed length, and let y be the height it reaches up the wall. Now y clearly depends on x. It is easy to see that if we pull the bottom end A a bit further from the wall, the top end B will come down a little lower. Let us state this in scientific language. If we increase x to x plus dx, then y will become y minus dy. That is, when x receives a positive increment, the increment which results to y is negative. Yes, but how much? Suppose the ladder was so long that when the bottom end A was 19 inches from the wall, the top end B reached just 15 feet from the ground. Now, if you were to pull the bottom end out 1 inch more, how much would the top end come down? Put it all into inches. X equals 19 inches, y equals 180 inches. Now the increment of x, which we call dx, is 1 inch, or x plus dx equals 20 inches. How much will y be diminished? The new height will be y minus dy. If we work out the height by Euclid 1:47, then we shall be able to find how much dy will be. The length of the ladder is the square root of the sum 180 squared plus 19 squared equals 181 inches. Clearly then, the new height, which is y minus dy, will be such that the difference y minus dy squared equals 181 squared minus 20 squared equals 32,761 minus 400 equals 32,361. Y minus dy equals the square root of 32,361 equals 179.89 inches. Now y is 180, so that dy is 180 minus 179.89 equals 0.11 inch. So we see that making dx an increase of 1 inch has resulted in making dy a decrease of 0.11 inch. And the ratio of dy to dx may be stated thus. dy over dx is equal to negative 0.11 over 1. It is also easy to see that, except in one particular position, dy will be of a different size from dx. Now right through the differential calculus we are hunting for a curious thing, a mere ratio, namely the proportion which dy bears to dx when both of them are indefinitely small. It should be noted here that we can only find this ratio dy over dx when y and x are related to each other in some way, so that whenever x varies, y does vary also. For instance, in the first example just taken, if the base x of the triangle be made longer, the height y of the triangle becomes greater also. And in the second example, if the distance x of the foot of the ladder from the wall be made to increase, the height y reached by the ladder decreases in a corresponding manner, slowly at first, but more and more rapidly as x becomes greater. In these cases, the relation between x and y is perfectly definite. It can be expressed mathematically, being y over x equals tangent 30 degrees, and x squared plus y squared equals L squared, where L is the length of the ladder respectively, and dy over dx has the meaning we found in each case. If, while x is, as before, the distance of the foot of the ladder from the wall, y is, instead of the height reached, the horizontal length of the wall, or the number of bricks in it, or the number of years since it was built, any change in x would naturally cause no change whatever in y. In this case, dy over dx has no meaning whatever, and it is not possible to find an expression for it. Whenever we use differentials dx, dy, dz, etc., the existence of some kind of relation between x, y, z, etc. is implied, and this relation is called a function in x, y, z, etc. The two expressions given above, for instance, namely y over x equals tangent 30 degrees, and x squared plus y squared equals L squared, are functions of x and y. Such expressions contain implicitly, that is, contain without distinctly showing it, the means of expressing either x in terms of y or y in terms of x. And for this reason they are called implicit functions in x and y. They can be respectively put into the forms y equals x times tangent 30 degrees, or x equals y over tangent 30 degrees, and y equals square root of the difference L squared minus x squared, or x equals square root of the difference L squared minus y squared. These last expressions state explicitly, that is distinctly, the value of x in terms of y, or of y in terms of x, and they are for this reason called explicit functions of x or y. For example, x squared plus 3 equals 2y minus 7 is an implicit function in x and y. It may be written y equals the quantity x squared plus 10 over 2, explicit function of x, or x equals square root of the difference to y minus 10, explicit function of y. We see that an explicit function in x, y, z, etc. is simply something the value of which changes when x, y, z, etc. are changing, either one at the time or several together. Because of this, the value of the explicit function is called the dependent variable, as it depends on the value of the other variable quantities in the function. These other variables are called the independent variables, because their value is not determined from the value assumed by the function. For example, if u equals x squared times sine theta, x and theta are the independent variables, and u is the dependent variable. Sometimes the exact relation between several quantities x, y, z either is not known, or it is not convenient to state it. It is only known or convenient to state that there is some sort of relation between these variables, so that one cannot alter either x or y or z singly without affecting the other quantities. The existence of a function in x, y, z is then indicated by the notation capital F of x, y, z, implicit function, or by x equals capital F of y and z, y equals capital F of x and z, or z equals capital F of x and y, explicit function. Sometimes the letter lowercase f or phi is used instead of uppercase F, so that y equals uppercase f of x, y equals lowercase f of x, and y equals phi of x, all mean the same thing, namely, that the value of y depends on the value of x in some way which is not stated. We call the ratio dy over dx the differential coefficient of y with respect to x. It is a solemn scientific name for this very simple thing. But we are not going to be frightened by solemn names, when the things themselves are so easy. Instead of being frightened, we will simply pronounce a brief curse on the stupidity of giving long, crack-jaw names, and, having relieved our minds, we'll go on to the simple thing itself, namely the ratio dy over dx. In ordinary algebra, which you learned at school, you were always hunting after some unknown quantity which you called x or y. Or sometimes there were two unknown quantities to be hunted for simultaneously. You have now to learn to go hunting in a new way, the fox being now neither x nor y. Instead of this, you have to hunt for this curious cub called dy over dx. The process of finding the value of dy over dx is called differentiating. But remember, what is wanted is the value of this ratio when both dy and dx are themselves indefinitely small. The true value of the differential coefficient is that to which it approximates in the limiting case when each of them is considered as infinitesimally minute. Let us now learn how to go in quest of dy over dx. Note to Chapter 3. How to read differentials. It will never do to fall into the schoolboy error of thinking that dx means d times x, for d is not a factor. It means an element of, or a bit of, whatever follows. One reads dx thus, dx. In case the reader has no one to guide him in such matters, it may here be simply said that one reads differential coefficients in the following way. The differential coefficient dy over dx is read dy by dx or dy over dx. So also du over dt is read du by dt. Second differential coefficients will be met with later on. They are like this: d superscript 2y over d x superscript 2, which is read d2y over dx squared. And it means that the operation of differentiating y with respect to x has been or has to be performed twice over. Another way of indicating that a function has been differentiated is by putting an accent to the symbol of the function. Thus, if y equals capital F of x, which means that y is some unspecified function of x, see page 13, we may write capital F prime of x instead of d capital F of x over dx. Similarly, capital F double prime of x will mean that the original function capital F of x has been differentiated twice over with respect to x. End of section 3. Section 4 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Simplest cases. Now, let us see how, on first principles, we can differentiate some simple algebraical expression. Case 1. Let us begin with the simple expression y equals x squared. Now remember that the fundamental notion about the calculus is the idea of growing. Mathematicians call it varying. Now, as y and x squared are equal to one another, it is clear that if x grows, x squared will also grow. And if x squared grows, then y will also grow. What we have got to find out is the proportion between the growing of y and the growing of x. In other words, our task is to find out the ratio between dy and dx, or, in brief, to find the value of dy over dx. Let x then grow a little bit bigger and become x plus dx. Similarly, y will grow a bit bigger and will become y plus dy. Then, clearly, it will still be true that the enlarged y will be equal to the square of the enlarged x. Writing this down, we have y plus dy equals the quantity x plus dx squared. Doing the squaring, we get y plus dy equals x squared plus 2x times dx plus dx squared. What does dx squared mean? Remember that dx meant a little bit of x. Then dx squared will mean a little bit of x. That is, as explained above, page 4, it is a small quantity of the second order of smallness. It may therefore be discarded as quite inconsiderable in comparison with the other terms. Leaving it out, we then have y plus dy equals x squared plus 2x times dx. Now y equals x squared. So let us subtract this from the equation, and we have left dy equals 2x times dx. Dividing across by dx, we find dy over dx equals 2x. Now this is what we set out to find. Note: this ratio dy over dx is the result of differentiating y with respect to x. Differentiating means finding the differential coefficient. Suppose we had some other function of x, as for example, u equals 7x squared plus 3. Then, if we were told to differentiate this with respect to x, we should have to find du over dx, or, what is the same thing, d, the quantity 7x squared plus 3, over dx. On the other hand, we may have a case in which time was the independent variable, see page 14, such as this: y equals b plus the fraction 1/2 a t squared. Then, if we were told to differentiate it, that means we must find its differential coefficient with respect to t. So that then our business would be to try to find dy over dt, that is, to find d, the quantity, b plus the fraction 1/2 a t squared over dt. End of note. The ratio of the growing of y to the growing of x is, in the case before us, found to be 2x. Numerical example. Suppose x equals 100, and therefore y equals 10,000. Then let x grow till it becomes 101. That is, let dx equal 1. Then the enlarged y will be 101 times 101 equals 10,201. But if we agree that we may ignore small quantities of the second order, 1 may be rejected as compared with 10,000. So we may round off the enlarged y to 10,200. Y has grown from 10,000 to 10,200. The bit added on is dy, which is therefore 200. dy over dx equals 200 over 1 equals 200. According to the algebra working of the previous paragraph, we find dy over dx equals 2x. And so it is, for x equals 100 and 2x equals 200. But, you will say, we neglected a whole unit. Well, try again, making dx a still smaller bit. Try dx equals the fraction 1/10. Then x plus dx equals 100.1. And the quantity x plus dx squared equals 100.1 times 100.1 equals 10,020.01. Now the last figure 1 is only 1/1,000,000th part of the 10,000, and is utterly negligible. so we may take 10,020 without the little decimal at the end. And this makes dy equals 20. And dy over dx equals 20 over 0.1 equals 200, which is still the same as 2x. Case 2. Try differentiating y equals x cubed in the same way. We let y grow to y plus dy, while x grows to x plus dx. Then we have y plus dy equals the quantity x plus dx cubed. Doing the cubing, we obtain y plus dy equals x cubed plus 3x squared times dx plus 3x times dx squared plus dx cubed. Now we know that we may neglect small quantities of the second and third orders, since when dy and dx are both made indefinitely small, dx squared and dx cubed will become indefinitely smaller by comparison. So regarding them as negligible, we have left y plus dy equals x cubed plus 3x squared times dx. But y equals x cubed, and subtracting this, we have dy equals 3x squared times dx, and dy over dx equals 3x squared. Case 3. Try differentiating y equals x raised to the fourth power. Starting as before by letting both y and x grow a bit, we have y plus dy equals the quantity x plus dx raised to the fourth power. Working out the raising to the fourth power, we get y plus dy equals x raised to the fourth power plus 4x cubed times dx plus 6x squared times dx squared plus 4x times dx cubed plus dx raised to the fourth power. Then striking out the terms containing all the higher powers of dx as being negligible by comparison, we have y plus dy equals x raised to the fourth power plus 4x cubed times dx. Subtracting the original y equals x to the fourth power, we have left dy equals 4x cubed times dx, and dy over dx equals 4x cubed. Now all these cases are quite easy. Let us collect the results to see if we can infer any general rule. Put them in two columns, the values of y in one and the corresponding values found for dy over dx in the other. Thus, when y is x squared, dy over dx is 2x. When y is x cubed, dy over dx is 3x squared. When y is x raised to the fourth power, dy over dx is 4x cubed. Just look at these results. The operation of differentiating appears to have had the effect of diminishing the power of x by 1. For example, in the last case, reducing x raised to the fourth power to x cubed, and at the same time multiplying by a number, the same number, in fact, which originally appeared as the power. Now, when you have once seen this, you might easily conjecture how the others will run. You would expect that differentiating x raised to the fifth power would give 5x raised to the fourth power, or differentiating x raised to the sixth power would give 6x raised to the fifth power. If you hesitate, try one of these and see whether the conjecture comes right. Try y equals x raised to the fifth power. Then, y plus dy equals the quantity x plus dx raised to the fifth power equals x raised to the fifth power plus 5x raised to the fourth power times dx plus 10x cubed times dx squared plus 10x squared times dx cubed plus 5x times dx raised to the fourth power plus dx raised to the fifth power. Neglecting all the terms containing small quantities of the higher orders, we have left y plus dy equals x raised to the fifth power plus 5x raised to the fourth power times dx. And subtracting y equals x raised to the fifth power leaves us dy equals 5x raised to the fourth power times dx, whence dy over dx equals 5x raised to the fourth power, exactly as we supposed. Following out logically our observation, we should conclude that if we want to deal with any higher power, call it n, we could tackle it in the same way. Let y equal x raised to the n power. Then we should expect to find that dy over dx equals n x raised to the n minus 1 power. For example, let n equal 8. Then y equals x raised to the 8th power, and differentiating it would give dy over dx equals 8x raised to the 7th power. And indeed, the rule that differentiating x raised to the n power gives, as the result, nx raised to the n minus 1 power is true for all cases where n is a whole number and positive. Expanding the quantity x plus dx raised to the n power by the binomial theorem will at once show this. But the question whether it is true for cases where n has negative or fractional values requires further consideration. Case of a negative power. Let y equal x to the minus 2. Then proceed as before. Y plus dy equals the quantity x plus dx to the minus 2 equals x to the minus 2 times the quantity 1 plus dx over x to the minus 2. Expanding this by the binomial theorem, see page 137, we get equals x to the minus 2 times the quantity 1 minus 2 dx over x plus 2 times the quantity 2 plus 1 over 1 times 2. That fraction times the quantity dx over x squared minus etc. equals x to the minus 2 minus 2x to the minus 3 times dx plus 3x to the minus 4 times dx squared minus 4x to the minus 5 times dx cubed plus etc. So, neglecting the small quantities of higher orders of smallness, we have y plus dy equals x to the minus 2 minus 2x to the minus 3 times dx. Subtracting the original y equals x to the minus 2, we find dy equals negative 2x to the minus 3 times dx. dy over dx equals negative 2x to the minus 3. And this is still in accordance with the rule inferred above. Case of a fractional power. Let y equal x to the 1/2. Then, as before, y plus dy equals the quantity x plus dx to the 1/2 equals x to the 1/2 times the quantity 1 plus dx over x to the 1/2 equals the square root of x plus 1/2 times dx over the square root of x minus 1/8 times dx squared over x times the square root of x plus terms with higher powers of dx. Subtracting the original y equals x to the 1/2 and neglecting higher powers, we have left dy equals 1/2 times dx over the square root of x equals 1/2 x to the minus 1/2 times dx. And dy over dx equals 1/2 x to the minus 1/2. Agreeing with the general rule. Summary. Let us see how far we have got. We have arrived at the following rule. To differentiate x raised to the n power, multiply by the power and reduce the power by 1, so giving us n x raised to the n minus 1 power as the result. End of section 4.
Section 5 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam. Calculus Made Easy by Silvanus P. Thompson, Section 5. Exercises 1. Differentiate the following. 1. Y equals x to the power of 13. Answer. dy by dx equals 13x to the power of 12. 2. Y equals x to the power of negative 3/2. Answer. dy by dx equals negative 3/2 x to the power of negative 5/2. 3. Y equals x to the power of 2a. Answer. dy by dx equals 2ax to the power of 2a minus 1. 4. U equals t to the power of 2.4. Answer. du by dt equals 2.4 t to the power of 1.4. 5. Z equals the cube root of u. Answer. dz by du equals 1/3 u to the power of negative 2/3. 6. Y equals the cube root of x to the negative 5. Answer. dy by dx equals negative 5/3 x to the power of negative 8/3. 7. U equals the fifth root of 1 over x to the 8th. Answer. du by dx equals negative 8/5 x to the power of negative 13/5. 8. Y equals 2x to the power of a. Answer. dy by dx equals 2a x to the power of a minus 1. 9. Y equals the qth root of x to the 3rd. Answer. dy by dx equals 3 over q times x to the power of 3 minus q over q. 10. Y equals the nth root of 1 over x to the m. Answer. dy by dx equals negative m over n x to the power of negative m plus n over n. You have now learned how to differentiate powers of x. How easy it is. End of section 5.
Section 6 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Chapter 5. Next stage. What to do with constants. In our equations, we have regarded x as growing, and as a result of x being made to grow, y also changed its value and grew. We usually think of x as a quantity that we can vary, and, regarding the variation of x as a sort of cause, we consider the resulting variation of y as an effect. In other words, we regard the value of y as depending on that of x. Both x and y are variables, but x is the one that we operate upon, and y is the dependent variable. In all the preceding chapter, we have been trying to find out rules for the proportion which the dependent variation in y bears to the variation independently made in x. Our next step is to find out what effect on the process of differentiating is caused by the presence of constants, that is, of numbers which don't change when x or y change their values. Added constants. Let us begin with some simple case of an added constant, thus, let y equal x cubed plus 5. Just as before, let us suppose x to grow to x plus dx and y to grow to y plus dy. Then, y plus dy equals the sum of x plus dx cubed plus 5 equals x cubed plus 3x squared times dx plus 3x times dx squared plus dx cubed plus 5. Neglecting the small quantities of higher orders, this becomes y plus dy equals x cubed plus 3x squared times dx plus 5. Subtract the original y equals x cubed plus 5, and we have left dy equal 3x squared dx. dy over dx equals 3x squared. So the 5 has quite disappeared. It added nothing to the growth of x and does not enter into the differential coefficient. If we had put 7 or 700 or any other number instead of 5, it would have disappeared. So if we take the letter A or B or C to represent any constant, it will simply disappear when we differentiate. If the additional constant had been of negative value, such as negative 5 or negative b, it would equally have disappeared. Multiplied constants. Take as a simple experiment this case. Let y equal 7x squared. Then on proceeding as before, we get y plus dy equals 7 times the quantity of x plus dx squared equals 7, left bracket, x squared plus 2x times dx plus the quantity dx squared, right bracket, equals 7x squared plus 14x times dx plus 7 times the quantity dx squared. Then, subtracting the original y equals 7x squared and neglecting the last term, we have dy equals 14x times dx. dy over dx equals 14x. Let us illustrate this example by working out the graphs of the equation y equals 7x squared and dy over dx equals 14x. By assigning to x a set of successive values 0, 1, 2, 3, etc., and finding the corresponding values of y and of dy over dx. These values we tabulate as follows. When x is 0, y is 0, dy over dx is 0. When x is 1, y is 7, dy over dx is 14. When x is 2, y is 28, dy over dx is 28. When x is 3, y is 63, dy over dx 42. When x is 4, y is 112, dy over dx is 56. When x is 5, y is 175, dy over dx is 70. When x is negative 1, y is 7, dy over dx is negative 14. When x is negative 2, y is 28, dy over dx is negative 28. When x is negative 3, y is 63, dy over dx is negative 42. Now, plot these values to some convenient scale, and we obtain the two curves of Figure 6 and 6a. Figure 6, graph of y equals 7x squared. X-axis is scaled negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. Y-axis scaled 0, 50, 100, 150, 200, with a curve through 0, 0, 1, 7, 2, 28, 3, 63, 4, and 112, 5, and 175, negative 1 and 7, negative 2 and 28, negative 3, 63. Figure 6a, graph of dy over dx equals 14x. X-axis scaled at negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. dy over dx axis scaled negative 50, 0, 50, 100, 150, with a curve through points 0, 0, 1, 14, 2, 28, 3, 42, 4, 56, 5, 70, negative 1, negative 14, negative 2, negative 28, negative 3, negative 42. Carefully compare the two figures and verify by inspection that the height of the ordinate of the derived curve, figure 6a, is proportional to the slope of the original curve, figure 6, at the corresponding value of x. Note: see page 76 about slopes of curves. To the left of the origin, where the original curve slopes negatively, that is downward from left to right, the corresponding ordinates of the derived curves are negative. Now, if we look back at page 18, we shall see that simply differentiating x squared gives us 2x, so that the differential coefficient of 7x squared is just 7 times as big as that of x squared. If we had taken 8x squared, the differential coefficient would have come out 8 times as great as that of x squared. If we put y equals ax squared, we shall get dy over dx equals a times 2x. If we had begun with y equals ax to the nth power, we should have had dy over dx equals a times nx to the n minus 1 power, so that any mere multiplication by a constant reappears as a mere multiplication when the thing is differentiated, and what is true about multiplication is equally true about division. For if, in the example above, we had taken as the constant 1/7 instead of 7, we should have had the same 1/7 come out in the result after differentiation. Some further examples. The following further examples, fully worked out, will enable you to master completely the process of differentiation as applied to ordinary algebraic expressions, and enable you to work out by yourself the examples given at the end of this chapter. Number 1. Differentiate. Y equals x to the 5th power over 7 minus 3 over 5. 3 over 5 is an added constant and vanishes. See page 25. We may then write at once dy over dx equals 1/7 times 5 times x to the 5 minus 1 power, or dy over dx equals 5/7 times x to the 4th power. Number 2. Differentiate y equals a square root of x minus 1/2 square root of a. The term 1/2 square root of a vanishes, being an added constant, and as a square root of x in the index form is written ax to the 1/2 power, we have dy over dx equals a times 1/2 times x to the 1/2 minus 1 power equals a over 2 times x to the negative 1/2 power, or dy over dx equals a over 2 times the square root of x. 3. If ay plus bx equals by minus ax plus the sum of x plus y times the square root of a squared minus b squared, find the differential coefficient of y with respect to x. As a rule, an expression of this kind will need a little more knowledge than we have acquired so far. It is, however, always worthwhile to try whether the expression can be put in a simpler form. First, we must try to bring it into the form y equals some expression involving x only. The expression may be written: the quantity a minus b times y plus the quantity a plus b times x equals the quantity x plus y times the square root of a squared minus b squared. Squaring, we get the quantity a minus b squared times y squared plus the quantity a plus b squared times x squared plus 2 times the quantity a plus b times the quantity a minus b times xy equals the quantity x squared plus y squared plus 2xy times the quantity a squared minus b squared, which simplifies to quantity a minus b squared y squared plus quantity a plus b squared x squared equals x squared times the quantity of a squared minus b squared plus y squared times the quantity of a squared minus b squared, or open bracket quantity a minus b squared minus quantity a squared minus b squared close bracket y squared equals open bracket quantity a squared minus b squared minus quantity a plus b squared close bracket x squared. That is 2b times the quantity of b minus a times y squared equals negative 2b times the quantity of b plus a times x squared. Hence, y equals the square root of a plus b over a minus b times x, and dy over dx equals the square root of a plus b over a minus b. Number 4. The volume of a cylinder of radius r and height h is given by the formula uppercase V equals pi r squared h. Find the rate of variation of volume with the radius when r equals 5.5 inches and h equals 20 inches. If r equal h, find the dimensions of the cylinder so that a change of 1 inch in radius causes a change of 400 cubic inches in the volume. the rate of variation uppercase V with regard to r is d uppercase V over dr equals 2 pi rh. If r equal 5.5 inches and h equal 20 inch, this becomes 690.8. It means that a change of radius of 1 inch will cause a change of volume of 690.8 cubic inch. This can be easily verified, for the volumes with r equal 5 and r equal 6 are 1,570 cubic inch and 2,260.8 cubic inch, respectively, and 2,260.8 minus 1,570 equals 690.8. Also, if r equal h, dv over dr equals 2 pi r squared equals 400, and r equals h equals the square root of 400 divided by 2 pi equals 7.98 inches. Number 5. The reading theta of Faraday's radiation parameter is related to the centigrade temperature T of the observed body by the relation theta over theta sub 1 equals the quantity T over T sub 1 to the fourth power, where theta sub 1 is the reading corresponding to a known temperature, T sub 1, of the observed body. Compare the sensitiveness of the parameter at temperatures 800 degrees centigrade, 1000 degrees centigrade, 1200 degrees centigrade, given that it read 25 when the temperature was 1000 degrees centigrade. The sensitiveness is the rate of variation of the reading with the temperature, that is, d theta over dt. The formula may be written theta equals theta sub 1 over t sub 1 to the fourth power times t to the fourth power equals 25t to the fourth power over 1000 to the fourth power. And we have d theta over dt equals 100t cubed over 1000 to the fourth power equals t cubed over 10 billion. When t equals 800, 1000, and 1200, we get d theta over dt equals 0.0512, 0.1, and 0.1728, respectively. The sensitiveness is approximately doubled from 800 degrees to 1000 degrees and becomes 3/4 as great again up to 1200 degrees. End of section 6.
Section 7 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 7. Exercises 2. Differentiate the following. Number 1. Y equals ax cubed plus 6. Answer. dy over dx equals 3ax squared. Number 2. Y equals 13x to the 3/2 power minus c. Answer. dy over dx equals 13 times 3/2 x to the 1/2 power. Number 3. Y equals 12x to the 1/2 power plus c to the 1/2 power. Answer. dy over dx equals 6x to the negative 1/2 power. Number 4. Y equals c to the 1/2 power times x to the 1/2 power. Answer: dy over dx equals 1/2 c to the 1/2 power times x to the negative 1/2 power. Number 5. U equals az to the nth power minus 1 over c. Answer: du over dz equals an over c times z to the n minus 1 power. Number 6. Y equals 1.18 t squared plus 22.4. Answer: dy over dt equals 2.36 t. Make up some other examples for yourself and try your hand at differentiating them. Number 7. If L sub t and L sub 0 be the lengths of a rod of iron at the temperatures of T degree centigrade and 0 degrees centigrade, respectively, then L sub t equals L sub 0, left parentheses, 1 plus 0.000012 t, right parentheses. Find the change of length of the rod per degree centigrade. Answer: dl sub t over dt equals 0.000012 times L sub 0. Number 8. It has been found that if C be the candle power of an incandescent electric lamp and capital V be the voltage, C equals A capital V to the B power, where A and B are constants. Find the rate of change of the candle power with the voltage and calculate the change of candle power per volt at 80, 100, and 120 volts in the case of a lamp for which A equals 0.5 times 10 to the negative 10 power and B equals 6. Answer: D uppercase C over D uppercase V equals AB uppercase V to the B minus 1 power, 0.98, 3.00, and 7.47 candle power per volt, respectively. Number 9. The frequency n of vibration of a string of diameter capital D, length capital L, and specific gravity sigma, stretched with the force capital T, is given by n equals 1 over capital D capital L times the square root of g capital T over pi sigma. Find the rate of change of the frequency when capital D, capital L, sigma, and capital T are varied singly. Answer: dn over d capital D equals negative 1 over capital L capital D squared times the square root of g capital T over pi sigma. dn over d capital L equals negative 1 over capital D capital L squared times square root of g capital T over pi sigma. dn over d sigma equals negative 1 over 2 capital D capital L times the square root of g capital T over pi sigma cubed. dn over d capital T equals 1 over 2 capital D capital L times the square root of g over pi sigma capital T. Number 10. The greatest external pressure, capital P, which a tube can support without collapsing, is given by capital P equals, left parentheses, 2 capital E over 1 minus sigma squared, end parentheses, times T cubed over capital D cubed, where capital E and sigma are constants. T is the thickness of the tube, and capital D is its diameter. This formula assumes that 4t is small compared to capital D. Compare the rate at which capital P varies for a small change of thickness and for a small change of diameter taking place separately. Answer: rate of change of capital P when t varies over rate of change of capital P when capital D varies equals negative capital D over t. Number 11. Find, from first principles, the rate at which the following vary with respect to a change in radius. A. The circumference of a circle of radius r. B. The area of a circle of radius r. C. The lateral area of cone of slant dimension L. D. The volume of a cone of radius r and height h. E. The area of a sphere of radius r. F. The volume of a sphere of radius r. Answers: A. 2 pi. B. 2 pi r. C. Pi L. D. 2/3 pi r h. E. 8 pi r. F. 4 pi r squared. Number 12. The length capital L of an iron rod at the temperature capital T being given by capital L equals L sub T, left bracket, 1 plus 0.000012, left parentheses, capital T minus T, right parentheses, right bracket, where L sub T is the length at the temperature T. Find the rate of variation of the diameter, capital D, of an iron tire suitable for being shrunk on a wheel when the temperature, capital T, varies. Answer: D capital D over D capital T equals 0.000012 L sub T over pi. End of section 7. Section 8 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 6. Sums, Differences, Products, and Quotients. We have learned how to differentiate simple algebraical functions such as x squared plus c or ax to the fourth power, and we have now to consider how to tackle the sum of two or more functions. For instance, let y equal the quantity x squared plus c plus the quantity ax to the fourth power plus b. What will its dy over dx be? How are we to go to work on this new job? The answer to this question is quite simple. Just differentiate them, one after the other, thus: dy over dx equal 2x plus 4ax cubed. If you have any doubt whether this is right, try a more general case, working it by first principles, and this is the way. Let y equal u plus v, where u is any function of x and v any other function of x. Then, letting x increase to x plus dx, y will increase to y plus dy, and u will increase to u plus du, and v to v plus dv. And we shall have y plus dy equals u plus du plus v plus dv. Subtracting the original y equal u plus v, we get dy equal du plus dv. And dividing through by dx, we get dy over dx equal du over dx plus dv over dx. This justifies the procedure. You differentiate each function separately and add the results. So if now we take the example of the preceding paragraph and put in the values of the two functions, we shall have, using the notation shown, page 16, dy over dx equal d times the quantity x squared plus c all over dx plus d times the quantity ax to the fourth power plus b all over dx equal 2x plus 4ax cubed, exactly as before. If there were three functions of x, which we may call u, v, and w, so that y equal u plus v plus w, then dy over dx equal du over dx plus dv over dx plus dw over dx. As for subtraction, it follows at once, for if the function v had itself had a negative sign, its differential coefficient would also be negative, so that by differentiating y equal u minus v, we should get dy over dx equal du over dx minus dv over dx. But when we come to do with products, the thing is not quite so simple. Suppose we were asked to differentiate the expression y equal the quantity x squared plus c times the quantity ax to the fourth power plus b. What are we to do? The result will certainly not be 2x times 4ax cubed, for it is easy to see that neither c times ax to the fourth power nor x squared times b would have been taken into that product. Now, there are two ways in which we may go to work. First way, do the multiplying first, and, having worked it out, then differentiate. Accordingly, we multiply together x squared plus c and ax to the fourth power plus b. This gives ax to the sixth power plus acx to the fourth power plus bx squared plus bc. Now differentiate, and we get dy over dx equal 6ax to the fifth power plus 4acx cubed plus 2bx. Second way. Go back to first principles and consider the equation y equal u times v. where u is one function of x and v is another function of x. Then, if x grows to be x plus dx and y to y plus dy, and u becomes u plus du, and v becomes v plus dv, we shall have y plus dy equal the quantity u plus du times the quantity v plus dv, equal u times v plus u times dv plus v times du plus du times dv. Now, du times dv is a small quantity of the second order of smallness, and therefore in the limit may be discarded, leaving y plus dy equal u times v plus u times dv plus v times du. Then, subtracting the original y equal u times v, we have left dy equal u times dv plus v times du. And, dividing through by dx, we get the result dy over dx equal u times dv over dx plus v times du over dx. This shows that our instructions will be as follows. To differentiate the product of two functions, multiply each function by the differential coefficient of the other, and add together the two products so obtained. You should note that this process amounts to the following. Treat u as a constant while you differentiate v. Then treat v as a constant while you differentiate u. And the whole differential coefficient, dy over dx, will be the sum of these two treatments. Now, having found this rule, apply it to the concrete example which was considered above. We want to differentiate the product quantity x squared plus c times quantity ax to the fourth power plus b. Call quantity x squared plus c equal u and quantity ax to the fourth power plus b equal v. Then, by the general rule just established, we may write dy over dx equal quantity x squared plus c times d times the quantity ax to the fourth power plus b all over dx plus quantity ax to the fourth power plus b times d times the quantity x squared plus c all over dx equal quantity x squared plus c times 4ax cubed plus quantity ax to the fourth power plus b times 2x equal 4ax to the fifth power plus 4acx cubed plus 2ax to the fifth power plus 2bx. dy over dx equal 6ax to the fifth power plus 4acx cubed plus 2bx, exactly as before. Lastly, we have to differentiate quotients. Think of this example. Y equal bx to the fifth power plus c over x squared plus a. In such a case, it is no use to try to work out the division beforehand, because x squared plus a will not divide into bx to the fifth power plus c. Neither have they any common factor. So there is nothing for it but to go back to first principles and find a rule. So we will put y equal u over v, where u and v are two different functions of the independent variable x. Then, when x becomes x plus dx, y will become y plus dy, and u will become u plus du, and v will become v plus dv. So then, y plus dy equal u plus du over v plus dv. Now, perform the algebraic division thus. V plus dv divided into u plus du equals u over v plus du over v minus u times dv over v squared by multiplying u over v by v plus dv and subtract the product u plus u times dv over v equals du minus u times dv over v. Subtract the product of v plus dv times du over v equals du plus du times dv over v equals negative u times dv over v minus du times dv over v. Subtract the product of v plus dv times u times dv over v squared equals negative u times dv over v minus u times dv over v squared equals negative du times dv over v plus u times dv over v squared. As both these remainders are small quantities of the second order, they may be neglected, and the division may stop here, since any further remainder would be of still smaller magnitudes. So we have got y plus dy equal u over v plus du over v minus u times dv over v squared, which may be written equals u over v plus v times du minus u times dv all over v squared. Now subtract the original y equals u over v, and we have left dy equal v times du minus u times dv all over v squared, whence dy over dx equal v times du over dx minus u times dv over dx all over v squared. This gives us our instructions as to how to differentiate a quotient of two functions. Multiply the divisor function by the differential coefficient of the dividend function, then multiply the dividend function by the differential coefficient of the divisor function, and subtract. Lastly, divide by the square of the divisor function. Going back to our example, y equal bx to the fifth power plus c over x squared plus a. Write bx to the fifth power plus c equal u, and x squared plus a equal v. Then dy over dx equal quantity x squared plus a times d times the quantity bx to the fifth power plus c all over dx minus the quantity bx to the fifth power plus c times d times the quantity x squared plus a all over dx all over the quantity squared x squared plus a equals the quantity x squared plus a times 5bx to the fourth power minus the quantity bx to the fifth power plus c times 2x all over the quantity squared x squared plus a. dy over dx equal 3bx to the sixth power plus 5abx to the fourth power minus 2cx all over the quantity squared x squared plus a. Answer. The working out of quotients is often tedious, but there's nothing difficult about it. Some further examples fully worked out are given hereafter. 1. Differentiate y equal a over b squared times x cubed minus a squared over b times x plus a squared over b squared. Being a constant, a squared over b squared vanishes, and we have dy over dx equal a over b squared times 3 times x to the 3 minus 1 power minus a squared over b times 1 times x to the 1 minus 1 power. But x to the 1 minus 1 power equal x to the 0 power equal 1, so we get dy over dx equal 3a over b squared times x squared minus a squared over b. 2. Differentiate y equal 2a times the square root of bx cubed minus 3b times the cube root of a all over x minus 2 times the square root ab. Putting x in the index form, we get y equal 2a times the square root of b times x to the 3/2 power minus 3b times the cube root of a times x to the minus 1 power minus 2 times the square root of ab. Now, dy over dx equal 2a times the square root of b times 3/2 times x to the 3/2 minus 1 power minus 3b times the cube root of a times -1 times x to the -1 minus 1 power. Or dy over dx equal 3a times the square root of bx plus 3b times the cube root of a all over x squared. 3. Differentiate z equal 1.8 times the cube root of 1 over theta squared minus 4.4 over the fifth root of theta minus 27 degrees. This may be written z equal 1.8 times theta to the -2/3 power minus 4.4 theta to the -1/5 power minus 27 degrees. The 27 degrees vanishes, and we have dz over d theta equal 1.8 times -2/3 times theta to the -2/3 minus 1 power minus 4.4 times -1/5 times theta to the -1/5 minus 1 power. Or dz over d theta equal -1.2 theta to the -5/3 power plus 0.88 theta to the -6/5 power. Or dz over d theta equal 0.88 over the fifth root of theta to the 6th power minus 1.2 over the cubed root of theta to the 5th power. 4. Differentiate v equal the quantity cubed 3t squared minus 1.2t plus 1. A direct way of doing this will be explained later. See page 66. But we can nevertheless manage it now without any difficulty. Developing the cube, we get v equal 27t to the 6th power minus 32.4t to the 5th power plus 39.96t to the 4th power minus 23.328t cubed minus 13.32t squared minus 3.6t plus 1. Hence, dv over dt equal 162t to the 5th power minus 162t to the 4th power plus 159.84t cubed minus 69.984t squared plus 26.64t minus 3.6. 5. Differentiate y equal quantity 2x minus 3 times the quantity squared x plus 1. dy over dx equal the quantity 2x minus 3 times d times the quantity of quantity x plus 1 times x plus 1 all over dx plus the quantity squared x plus 1 times d times the quantity 2x minus 3 all over dx equal the quantity 2x minus 3 times, open bracket, quantity x plus 1 times d times the quantity x plus 1 all over dx plus the quantity x plus 1 times d times the quantity x plus 1 all over dx, close bracket, plus the quantity squared x plus 1 times d times the quantity 2x minus 3 all over dx, equal 2 times the quantity x plus 1 times the quantity 2x minus 3 plus quantity x plus 1 equals 2 times the quantity x plus 1 times the quantity 3x minus 2. Or, more simply, multiply out and then differentiate. 6. Differentiate y equal 0.5 x cubed times the quantity x minus 3. dy over dx equal 0.5 times the quantity x cubed times d times the quantity x minus 3 all over dx plus the quantity x minus 3 times d times x cubed all over dx equal 0.5 times the quantity x cubed plus quantity x minus 3 times 3x squared equal 2x cubed minus 4.5x squared. Same remarks as for preceding example. 7. Differentiate w equal the quantity theta plus 1 over theta times the quantity square root of theta plus 1 over the square root of theta. This may be written w equal the quantity theta plus theta to the negative 1 power times the quantity theta to the 1/2 power plus theta to the negative 1/2 power. dw over d theta equal quantity theta plus theta to the negative 1 power times d times the quantity theta to the 1/2 power plus theta to the negative 1/2 power all over d theta plus quantity theta to the 1/2 power plus theta to the negative 1/2 power times d times quantity theta plus theta to the negative 1 power all over d theta equal quantity theta plus theta to the negative 1 power times quantity 1/2 theta to the negative 1/2 power minus 1/2 theta to the negative 3/2 power plus the quantity theta to the 1/2 power plus theta to the negative 1/2 power times 1 minus theta to the negative 2 power equal 1/2 times the quantity theta to the 1/2 power plus theta to the negative 3/2 power minus theta to the negative 1/2 power minus theta to the negative 5/2 power plus the quantity theta to the 1/2 power plus theta to the negative 1/2 power minus theta to the negative 3/2 power minus theta to the negative 5/2 power equal 3/2 times the quantity square root of theta minus 1 over the square root of theta to the 5th power plus 1/2 times the quantity 1 over the square root of theta minus 1 over the square root of theta cubed. This, again, could be obtained more simply by multiplying the two factors first and differentiating afterwards. This is not, however, always possible. See, for instance, page 170, example 8, in which the rule for differentiating a product must be used. 8. Differentiate y equal a over 1 plus a times the square root of x plus a squared x. dy over dx equal the quantity 1 plus ax to the 1/2 power plus a squared times x times 0 minus a times d times the quantity 1 plus ax to the 1/2 power plus a squared x all over dx all over quantity squared 1 plus a times the square root of x plus a squared x equal negative a times the quantity 1/2 ax to the negative 1/2 plus a squared all over the quantity squared 1 plus ax to the 1/2 power plus a squared x. 9. Differentiate y equal x squared over x squared plus 1. dy over dx equal the quantity x squared plus 1 times 2x minus x squared times 2x all over the quantity squared x squared plus 1 equal 2x over the quantity squared x squared plus 1. 10. Differentiate y equal a plus the square root of x all over a minus the square root of x. In the index form, y equal a plus x to the 1/2 power all over a minus x to the 1/2 power, dy over dx equal the quantity a minus x to the 1/2 power times the quantity 1/2 x to the negative 1/2 power minus the quantity a plus x to the 1/2 power times the quantity negative 1/2 x to the negative 1/2 power all over the quantity squared a minus x to the 1/2 power equal a minus x to the 1/2 power plus a plus x to the 1/2 power all over 2 times the quantity squared a minus x to the 1/2 power times x to the 1/2 power. Hence, dy over dx equal a over the quantity squared a minus the square root of x times the square root of x. 11. Differentiate. Theta equals 1 minus a times the cubed root of t squared all over 1 plus a times the square root of t cubed. Now, theta equals 1 minus at to the 2/3 power all over 1 plus at to the 3/2 power. d theta over dt equal the quantity 1 plus at to the 3/2 power times the quantity negative 2/3 at to the negative 1/3 power minus the quantity 1 minus at to the 2/3 power times 3/2 at to the 1/2 power all over the quantity squared 1 plus at to the 3/2 power equal 5a squared times the 6th root of t to the 7th power minus 4a over the cubed root of t minus 9a times the square root of t all over 6 times the quantity squared 1 plus a times the square root of t cubed. 12. A reservoir of square cross-section has sides sloping at an angle of 45 degrees with the vertical. The side of the bottom is 200 feet. Find an expression for the quantity pouring in or out when the depth of water varies by 1 foot. Hence find, in gallons, the quantity withdrawn hourly when the depth is reduced from 14 to 10 feet in 24 hours. The volume of a frustum of pyramid of height uppercase H and of bases uppercase A and lowercase a is uppercase V equals uppercase H over 3 times the quantity uppercase A plus lowercase a plus the square root of uppercase A times lowercase a. It is easily seen that the slope being 45 degrees, if the depth be lowercase h, the length of the side of the square surface of the water is 200 plus 2 lowercase h feet, so that the volume of water is lowercase h over 3 times the quantity 200 squared plus the quantity squared 200 plus 2 lowercase h plus 200 times the quantity 200 plus 2 times lowercase h equals 40,000 lowercase h plus 400 h squared plus 4h cubed over 3. D uppercase V over D lowercase h equal 40,000 plus 800h plus 4h squared equal cubic feet per foot of depth variation. The mean level from 14 to 10 feet is 12 feet. when lowercase h equals 12, d times uppercase v over d over lowercase h equals 50,176 cubic feet. Gallons per hour corresponding to a change of depth of 4 feet in 24 hours equals 4 times 50,176 times 6.25 all over 24 equals 52,267 gallons. 13. The absolute pressure in atmospheres, uppercase P, of saturated steam at the temperature T degrees centigrade is given by DeLong as being uppercase P equals the quantity to the fifth power 40 plus T over 140, as long as T is above 80 degrees. Find the rate of variation of the pressure with the temperature at 100 degrees centigrade. Expand the numerator by the binomial theorem, see page 137. Uppercase P equals 1 over 140 to the fifth power times the quantity 40 to the fifth power plus 5 times 40 to the fourth power T plus 10 times 40 cubed times T squared plus 10 times 40 squared T cubed plus 5 times 40t to the fourth power plus t to the fifth power. Hence, d uppercase P over dt equals 1 over 537,824 times 10 to the fifth power times the quantity 5 times 40 to the fourth power plus 20 times 40 cubed t plus 30 times 40 squared t squared plus 20 times 40t cubed plus 5t to the fourth power. When t equals 100, this becomes 0.036 atmosphere per degree centigrade change of temperature. End of section 8.
Section 9 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga, Ontario, pjk.scripps.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson. Section 9. Exercises 3. Exercise 1. Differentiate. Question A. U equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... Answer. 1 plus x squared over 2 plus x cubed over 6 plus x4 over 24 plus ... Question B. Y equals ax squared plus bx plus c. Answer. 2ax plus b. Question C. Y equals x plus a quantity squared. Answer. 2x plus 2a. Question D. Y equals x plus a quantity cubed. Answer. 3x squared plus 6ax plus 3a squared. Question 2. If w equals at plus 1/2 bt squared, find dw by dt. Answer. dw by dt equals a minus bt. Question 3. Find the differential coefficient of y equals the quantity x plus the square root of minus 1 multiplied by the quantity x minus the square root of minus 1. Answer. dy by dx equals 2x. Question 4. Differentiate. y equals open bracket 197x minus 34x squared close bracket multiplied by open bracket 7 plus 22x minus 83x cubed close bracket. Answer 14,110 x to the fourth minus 65,404 x cubed minus 2,244 x squared plus 8,192 x plus 1,379. Question 5. If x equals open bracket y plus 3 close bracket multiplied by open bracket y plus 5 close bracket, find dx by dy. Answer dx by dy equals 2y plus 8. Question 6. Differentiate y equals 1.3709x multiplied by open bracket 112.6 plus 45.202x squared close bracket. Answer 185.9022654x squared plus 154.36334. Question 7. Find the differential coefficients of y equals the quantity 2x plus 3 divided by the quantity 3x plus 2. Answer negative 5 divided by open bracket 3x plus 2 close bracket all squared. Question 8. Find the differential coefficients of y equals the quantity 1 plus x plus 2x squared plus 3x cubed divided by the quantity 1 plus x plus 2x squared. Answer the quantity 6x to the fourth plus 6x cubed plus 9x squared all divided by open bracket 1 plus x plus 2x squared close bracket all squared. Question 9. Find the differential coefficients of y equals the quantity ax plus b divided by the quantity cx plus d. Answer the quantity ad minus bc divided by open bracket cx plus d close bracket all squared. Question 10. Y equals the quantity x to the power n plus a divided by the quantity x to the power of minus n plus b. Answer anx to the power of negative n minus 1 plus bnx to the power of n minus 1 plus 2nx to the power of minus 1 all divided by open bracket x to the power of minus n plus b close bracket all squared. Question 11. The temperature T of the filament of an incandescent electric lamp is connected to the current passing through the lamp by the relation C equals A plus BT plus CT squared. Find an expression giving the variation of the current corresponding to a variation of temperature. Answer B plus 2CT. Question 12. The following formulae have been proposed to express the relation between the electric resistance R of a wire at the temperature T degrees Celsius and the resistance R naught of the same wire at 0 degrees centigrade, A, B, C being constants. R equals R naught times open bracket 1 plus AT plus BT squared close bracket. R equals R naught times open bracket 1 plus AT plus B times the square root of T close bracket. R equals R naught times open bracket 1 plus AT plus BT squared close bracket raised to the power minus 1. Find the rate of variation of the resistance with regard to temperature as given by each of these formulae. Answer R naught times open bracket A plus 2BT close bracket r naught times open bracket a plus b divided by 2 root t, close bracket. Negative r naught times open bracket a plus 2bt, close bracket, divided by open bracket 1 plus at plus bt squared, close bracket, squared. Or r squared times open bracket a plus 2bt, close bracket, divided by r naught. Question 13. The electromotive force E of a certain type of standard cell has been found to vary with the temperature T according to the relation E equals 1.4340 times open bracket 1 minus 0.000814 times open bracket T minus 15 closed bracket plus 0.000007 times open bracket T minus 15 closed bracket squared closed bracket volts. Find the change of electromotive force per degree at 15 degrees, 20 degrees, and 25 degrees. Answer: 1.4340 multiplied by open bracket 0.000014t minus 0.001024 close bracket, negative 0.00117, negative 0.00107, and finally negative 0.00097. Question 14. The electromotive force necessary to maintain an electric arc of length L with a current of intensity I has been found by Mrs. Ayrton to be E equals A plus BL plus the quantity C plus KL all divided by I, where A, K, B, and C are constants. Find an expression for the variation of the electromotive force A with regard to the length of the arc and B with regard to the strength of the current. Answers: dE by dL equals B plus K over I, and dE by dI equals negative C minus KL all divided by I squared. End of section 9. Section 10 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Paul King, Mississauga, Ontario. pjk.scripps.mit.edu/pkj. Calculus Made Easy by Silvanus P. Thompson. Section 10. Chapter 7. Successive Differentiation. Let us try the effect of repeating several times over the operation of differentiating a function. Begin with a concrete case. Let y equal x to the power 5. First differentiation, 5x to the power 4. Second differentiation, 5 times 4 times x to the power 3. That's equal to 20x cubed. Third differentiation, 5 times 4 times 3 times x squared, which is equal to 60x squared. Fourth differentiation, 5 times 4 times 3 times 2 times x, which is 120x. Fifth differentiation, 5 times 4 times 3 times 2 times 1 equals 120. Sixth differentiation, 0. There is a certain notation with which we already are acquainted, used by some writers, that is very convenient. This is to employ the general symbol f of x for any function of x. Here the symbol f followed by a pair of brackets is read as function of without saying what particular function is meant. So the statement y equals f of x merely tells us that y is a function of x. It may be x squared or ax to the n or cosine of x or any other complicated function of x. The corresponding symbol for the differential coefficient is f primed of x, which is simpler to write than dy by dx. This is called the derived function of x. Suppose we differentiate over again. We shall get the second derived function or second differential coefficient, which is denoted by f double prime of x, and so on. Now let's generalize. Let y equal f of x equal x to the power n. First differentiation, f prime of x equals n times x to the power n minus 1. Second differentiation, f double prime of x equals n times n minus 1 times x to the power n minus 2. Third differentiation, f triple prime of x equals n times n minus 1 times n minus 2 times x to the power n minus 3. Fourth differentiation, f quadruple prime of x equals n times n minus 1 times n minus 2 times n minus 3 times x to the power n minus 4, etc., etc. But this is not the only way of indicating successive differentiations. For if the original function be y equals f of x, once differentiating gives dy by dx equals f prime of x. Twice differentiating gives d by dy by dx equals f double prime of x. And this is more conveniently written as d squared y by dx quantity squared, or more usually as d squared y by dx squared. Similarly, we may write as the result of thrice differentiating d cubed y by dx cubed, or f triple primed of x. Examples. Now let us try y equals f of x equals 7x to the power 4 plus 3.5x to the power 3 minus 1 half x squared plus x minus 2. dy by dx, that's f primed of x, which is 28x cubed plus 10.5 x squared minus x plus 1. d squared y by dx squared equals f double primed of x equals 84x squared plus 21x minus 1. d cubed y by dx cubed equals the third derivative of x, which is equal to 168x plus 21. d to the fourth power y plus dx to the power 4 is the fourth derivative of x, which is equal to 168. And finally, d to the fifth y by dx to the fifth is the fifth derivative, which is 0. In a similar manner, if y equals phi of x equals 3x times the quantity x squared minus 4, then phi prime of x equals dy by dx equals 3 times the quantity x times 2x plus the quantity x squared minus 4 times 1, which equals 3 times the quantity 3x squared minus 4. Phi double primed of x is equal to d squared y by dx squared, which is equal to 3 times 6x, which is equal to 18x. Phi triple prime of x, which is equal to d cubed y by dx cubed, is equal to 18. And the fourth derivative, phi quadruple prime of x, is equal to d to the fourth y by dx fourth, which is 0. End of section 10.
Section 11 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 11. Exercises 4. Find dy over dx and d squared y all over dx squared for the following expressions. 1. Y equal 17x plus 12x squared. Answer: 17 plus 24x and 24. 2. Y equal x squared plus a over x plus a. Answer: x squared plus 2ax minus a all over the quantity squared x plus a, and 2a times the quantity a plus 1 all over the quantity cubed x plus a. 3. Y equal 1 plus x over 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3 plus x to the fourth power over 1 times 2 times 3 times 4. Answer: 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3, and 1 plus x squared over 1 times 2. 4. Find the second and third derived functions in the exercises 3, number 1 to number 7, and in the examples given, number 1 to number 7. Answers. Exercises 3. 1. A. D squared y over dx squared equals d cubed y over dx cubed equals 1 plus x plus 1/2 x squared plus 1/6 x cubed plus ellipsis. B. 2a and 0. C. 2 and 0. D. 6x plus 6a and 6. 2. Negative b and 0. 3. 2 and 0. 4. 56,440 x cubed minus 196,212 x squared minus 4,488x plus 8,192. 169,320 x squared minus 392,424 x minus 4,488. 5. 2, 0. 6. 371.80453x 371.80453. 7. 30 over the quantity cubed 3x plus 2 negative 270 over the quantity to the fourth power 3x plus 2. Examples, page 40. 1. 6a over b squared x 6a over b squared. 2. 3a square root of b over 2 square root of x minus 6b cubed root of a all over x cubed. 18b times the cubed root of a over x to the fourth power minus 3a times the square root of b all over 4 times the square root of x cubed. 3. 2 over the cubed root of theta to the 8th power minus 1.056 over the 5th root of theta to the 11th power, 2.3232 over the 5th root of theta to the 16th power minus 16 over 3 times the cube root of theta to the 11th power. 4. 810t to the 4th power minus 648t cubed plus 479.52t squared minus 139.968t plus 26.64. 3,240t cubed minus 1,944t squared plus 959.04t minus 139.968. 5. 12x plus 2, 12. 6. 6x squared minus 9x, 12x minus 9. 7. 3/4 times the quantity 1 over the square root of theta plus 1 over the square root of theta to the 5th power plus 1/4 times the quantity 15 over the square root of theta to the 7th power minus 1 over the square root of theta to the 3rd power. 3/8 times the quantity 1 over the square root of theta to the 5th power minus 1 over the square root of theta to the 3rd power minus 15 over 8 times the quantity 7 over the square root of theta to the 9th power plus 1 over the square root of theta to the 7th power. End of section 11.
Section 12 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jargoniel. Calculus Made Easy by Silvanus P. Thompson. Chapter 8, When Time Varies. Part 1. Some of the most important problems of the calculus are those where time is the independent variable, and we have to think about the values of some other quantity that varies when the time varies. Some things grow larger as time goes on. Some other things grow smaller. The distance that a train has got from its starting place goes on ever increasing as time goes on. Trees grow taller as the years go by. Which is growing at the greater rate? A plant 12 inches high, which in 1 month becomes 14 inches high, or a tree 12 feet high, which in a year becomes 14 feet high? In this chapter, we are going to make much use of the word rate. Nothing to do with pour rate or water rate, except that even here the word suggests a proportion, a ratio, so many pence in the pound. Nothing to do even with birth rate or death rate, though these words suggest so many births or deaths per thousand of the population. When a motor car whizzes by us, we say, "What a terrific rate!" When a spendthrift is flinging about his money, we remark that that young man is living at a prodigious rate. What do we mean by rate? In both these cases, we are making a mental comparison of something that is happening and the length of time that it takes to happen. If the motor car flies past us, going 10 yards per second, a simple bit of mental arithmetic will show us that this is the equivalent, while it lasts, to a rate of 600 yards per minute, or over 20 miles per hour. Now, in what sense is it true that a speed of 10 yards per second is the same as 600 yards per minute? 10 yards is not the same as 600 yards, nor is 1 second the same thing as 1 minute. What we mean by saying that the rate is the same is this: that the proportion borne between distance passed over and time taken to pass over it is the same in both cases. Take another example. A man may have only a few pounds in his possession, and yet be able to spend money at the rate of millions a year, provided he goes on spending money at that rate for a few minutes only. Suppose you hand a shilling over the counter to pay for some goods, and suppose the operation lasts exactly 1 second. Then, during that brief operation, you are parting with your money at the rate of 1 shilling per second, which is the same rate as 3 pounds per minute, or 180 pounds per hour, or 4,320 pounds per day, or 1,576,800 pounds per year. If you have 10 pounds in your pocket, you can go on spending money at the rate of 1 million a year for just 5 1/4 minutes. It is said that Sandy had not been in London above 5 minutes when bang went saxpence. If he were to spend money at that rate all day long, say for 12 hours, he would be spending 6 shillings an hour, or £3 12 shillings per day, or £21 12 shillings a week, not counting the Sabbath. Now try to put some of these ideas into differential notation. Let y in this case stand for money, and let t stand for time. If you are spending money, and the amount you spend in a short time dt be called dy, the rate of spending it will be dy over dt, or rather should be written with a minus sign as negative dy over dt, because dy is a decrement, not an increment. But money is not a good example for the calculus, because it generally comes and goes by jumps, not by a continuous flow. You may earn 200 pounds a year, but it does not keep running in all day long in a thin stream. It comes in only weekly, or monthly, or quarterly, in lumps, and your expenditure also goes out in sudden payments. A more apt illustration of the idea of a rate is furnished by the speed of a moving body. From London, Euston Station, to Liverpool is 200 miles. If a train leaves London at 7 o'clock and reaches Liverpool at 11 o'clock, you know that, since it has traveled 200 miles in 4 hours, its average rate must have been 50 miles per hour, because 200 divided by 4 equals 50 divided by 1. Here you are really making a mental comparison between the distance passed over and the time taken to pass over it. You are dividing one by the other. If y is the whole distance and t the whole time, clearly the average rate is y over t. Now the speed was not actually constant all the way. At starting and during the slowing up at the end of the journey, the speed was less. Probably at some part, when running downhill, the speed was over 60 miles an hour. If during any particular element of time, dt, the corresponding element of distance passed over was dy, then at that part of the journey the speed was dy over dt. The rate at which one quantity, in the present instance distance, is changing in relation to the other quantity, in this case time, is properly expressed, then, by stating the differential coefficient of one with respect to the other. A velocity, scientifically expressed, is the rate at which a very small distance in any given direction is being passed over, and may therefore be written v equals dy over dt. But if the velocity v is not uniform, then it must be either increasing or else decreasing. The rate at which a velocity is increasing is called the acceleration. If a moving body is, at any particular instant, gaining an additional velocity dv in an element of time dt, then the acceleration a, at that instant, may be written a equals dv over dt. But dv is itself d times dy over dt. Hence, we may put a equals d times dy over dt all over dt. And this is usually written a equals d squared y over dt squared, or the acceleration is the second differential coefficient of the distance with respect to time. Acceleration is expressed as a change of velocity in unit time. For instance, as being so many feet per second per second. The notation used being feet divided by seconds squared. When a railway train has just begun to move, its velocity v is small, but it is rapidly gaining speed. It is being hurried up or accelerated by the effort of the engine, so its d squared y over dt squared is large. When it has got up its top speed, it is no longer being accelerated, so that then d squared y over dt squared has fallen to 0. But when it nears its stopping place, its speed begins to slow down, may indeed slow down very quickly if the brakes are put on, and during this period of deceleration or slackening of pace, the value of dv over dt, that is, of d squared y over dt squared, will be negative. To accelerate a mass m requires the continuous application of force. The force necessary to accelerate a mass is proportional to the mass, and it is also proportional to the acceleration which is being imparted. Hence, we may write for the force F the expression F equals ma, or F equals m times dv over dt, or F equals m times d squared y over dt squared. The product of a mass by the speed at which it is going is called its momentum, and is in symbols mv. If we differentiate momentum with respect to time, we shall get d times mv all over dt for the rate of change of momentum. But since m is a constant quantity, this may be written m times dv over dt, which we see above is the same as F. That is to say, force may be expressed either as mass times acceleration or as rate of change of momentum. Again, if a force is employed to move something against an equal and opposite counterforce, it does work, and the amount of work done is measured by the product of the force into the distance, in its own direction, through which its point of application moves forward. So if a force F moves forward through a length y, the work done, which we may call W, will be W equals F times y, where we take F as a constant force. If the force varies at different parts of the range y, then we must find an expression for its value from point to point. If F be the force along the small element of length dy, the amount of work done will be F times dy. But as dy is only an element of length, only an element of work will be done. If we write W for work, then an element of work will be dW, and we have dW equals F times dy, which may be written dW equals ma times dy, or dW equals m times d squared y over dt squared times dy, or dW equals m times dv over dt times dy. Further, we may transpose the expression and write dW over dy equals F. This gives us yet a third definition of force, that if it is being used to produce a displacement in any direction, the force in that direction is equal to the rate at which work is being done per unit of length in that direction. In this last sentence, the word rate is clearly not used in its time sense, but in its meaning as ratio or proportion. Sir Isaac Newton, who was, along with Leibniz, an inventor of the methods of the calculus, regarded all quantities that were varying as flowing, and the ratio which we nowadays call the differential coefficient he regarded as the rate of flowing, or the fluxion of the quantity in question. He did not use the notation of the dy and dx and dt. This was due to Leibniz, but had instead a notation of his own. If y was a quantity that varied, or flowed, then his symbol for its rate of variation, or fluxion, was y dot. If x was the variable, then its fluxion was called x dot. The dot over the letter indicated that it had been differentiated, but this notation does not tell us what is the independent variable with respect to which the differentiation has been effected. When we see dy over dt, we know that y is to be differentiated with respect to t. If we see dy over dx, we know that y is to be differentiated with respect to x. But if we see merely y dot, we cannot tell without looking at the context whether this is to mean dy over dx, or dy over dt, or dy over dz, or what is the other variable. So therefore, this fluxional notation is less informing than the differential notation, and has in consequence largely dropped out of use. But its simplicity gives it an advantage, if only we will agree to use it for those cases exclusively where time is the independent variable. In that case, y dot will mean dy over dt, and u dot will mean du over dt, and x double dot will mean d squared x over dt squared. Adopting this fluxional notation, we may write the mechanical equations considered in the paragraphs above as follows. Distance, x. Velocity, v equals x dot. Acceleration, a equals v dot equals x double dot. Force, F equals mv dot equals mx double dot. Work, W equals x times mx double dot. End of section 12. Recording by Jargoniel. Section 13 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Jargoniel. Calculus Made Easy by Silvanus P. Thompson. Chapter 8, When Time Varies. Part 2. Examples. Example 1. A body moves so that the distance x in feet, which it travels from a certain point O, is given by the relation x equals 0.2 t squared plus 10.4, where t is the time in seconds elapsed since a certain instant. Find the velocity and acceleration 5 seconds after the body began to move, and also find the corresponding values when the distance covered is 100 feet. Find also the average velocity during the first 10 seconds of its motion. Suppose distances and motion to the right to be positive. Now, x equals 0.2 t squared plus 10.4. V equals x dot equals dx over dt, which equals 0.4 t. And A equals x double dot equals d squared x over dt squared, which equals 0.4, which equals constant. When t equals 0, x equals 10.4, and v equals 0. The body started from a point 10.4 feet to the right of the point O, and the time was reckoned from the instant the body started. When t equals 5, v equals 0.4 times 5, which equals 2 feet per second. A equals 0.4 feet per second squared. When x equals 100, 100 is equal to 0.2 t squared plus 10.4, or t squared equals 448, and t equals 21.17 seconds. V equals 0.4 times 21.17, which equals 8.468 feet per second. When t equals 10, distance traveled equals 0.2 times 10 squared plus 10.4 minus 10.4, which equals 20 feet. Average velocity equals 20 over 10, which equals 2 feet per second. It is the same velocity as the velocity at the middle of the interval t equals 5. For the acceleration being constant, the velocity has varied uniformly from 0 when t equals 0 to 4 feet per second when t equals 10. Example 2. In the above problem, let us suppose x is equal to 0.2 t squared plus 3t plus 10.4. V equals x dot equals dx over dt, which equals 0.4 t plus 3. A equals x double dot equals d squared x over dt squared, which equals 0.4, which equals constant. When t equals 0, x equals 10.4, and v equals 3 feet per second, the time is reckoned from the instant at which the body passed a point 10.4 feet from the point O, its velocity being then already 3 feet per second. To find the time elapsed since it began moving, let v equals 0, then 0.4t plus 3 equals 0. T equals negative 3 divided by 0.4, which equals negative 7.5 seconds. The body began moving 7.5 seconds before time was begun to be observed. 5 seconds after this gives t equals negative 2.5, and v equals 0.4 times negative 2.5 plus 3, which equals 2 feet per second. When x equals 100 feet, 100 equals 0.2t squared plus 3t plus 10.4, or t squared plus 15t minus 448, which equals 0. Hence, t equals 14.95 seconds. V equals 0.4 times 14.95 plus 3, which equals 8.98 feet per second. To find the distance traveled during the 10 first seconds of the motion, one must know how far the body was from the point O when it started. When t equals negative 7.5, x equals 0.2 times negative 7.5 squared minus 3 times 7.5 plus 10.4, which equals negative 0.85 feet. That is 0.85 feet to the left of the point O. Now, when t equals 2.5, x equals 0.2 times 2.5 squared plus 3 times 2.5 plus 10.4, which equals 19.15. So in 10 seconds, the distance traveled was 19.15 plus 0.85, which equals 20 feet, and the average velocity equals 20 over 10, which equals 2 feet per second. Example 3. Consider a similar problem when the distance is given by x equals 0.2t squared minus 3t plus 10.4. Then v equals 0.4t minus 3. A equals 0.4, which equals constant. When t equals 0, x equals 10.4, as before, and v equals negative 3, so that the body was moving in the direction opposite to its motion in the previous cases. As the acceleration is positive, however, we see that this velocity will decrease as time goes on, until it becomes 0, when v equals 0, or 0.4t minus 3 equals 0, or t equals 7.5 seconds. After this, the velocity becomes positive, and 5 seconds after the body started, t equals 12.5, and v equals 0.4 times 12.5 minus 3, which equals 2 feet per second. When x equals 100, 100 equals 0.2t squared minus 3t plus 10.4, or t squared minus 15t minus 448, which equals 0, and t equals 29.95, v equals 0.4 times 29.95 minus 3, which equals 8.98 feet per second. When v is 0, x equals 0.2 times 7.5 squared minus 3 times 7.5 plus 10.4, which equals negative 0.85, informing us that the body moves back to 0.85 feet beyond the point O before it stops. 10 seconds later, t equals 17.5 and x equals 0.2 times 17.5 squared minus 3 times 17.5 plus 10.4, which equals 19.15. The distance traveled is equal to 0.85 plus 19.15, which equals 20.0. And the average velocity is again 2 feet per second. Example 4. Consider yet another problem of the same sort with x equals 0.2t cubed minus 3t squared plus 10.4. v equals 0.6t squared minus 6t. a equals 1.2t minus 6. The acceleration is no more constant. When t equals 0, x equals 10.4, v equals 0, a equals negative 6. The body is at rest, but just ready to move with a negative acceleration. That is, to gain a velocity towards the point O. Example 5. If we have x equals 0.2t cubed minus 3t plus 10.4, then v equals 0.6t squared minus 3, and a equals 1.2t. When t equals 0, x equals 10.4, v equals negative 3, a equals 0. The body is moving towards the point O with a velocity of 3 feet per second, and just at that instant the velocity is uniform. We see that the conditions of the motion can always be at once ascertained from the time-distance equation and its first and second derived functions. In the last two cases, the mean velocity during the first 10 seconds and the velocity 5 seconds after the start will no more be the same, because the velocity is not increasing uniformly, the acceleration being no longer constant. Example 6. The angle theta in radians turned through by a wheel is given by theta equals 3 plus 2t minus 0.1t cubed, where t is the time in seconds from a certain instant. Find the angular velocity omega and the angular acceleration alpha, a, after 1 second, b, after it has performed 1 revolution. At what time is it at rest, and how many revolutions has it performed up to that instant? Writing for the acceleration, omega equals theta dot equals d theta over dt, which equals 2 minus 0.3t squared. Alpha equals theta double dot equals d squared theta over dt squared, which equals negative 0.6t. When t equals 0, theta equals 3, omega equals 2 radians per second, alpha equals 0. When t equals 1, omega equals 2 minus 0.3, which equals 1.7 radians per second. Alpha equals negative 0.6 radians per second squared. This is a retardation. The wheel is slowing down. After 1 revolution, theta equals 2 pi, which equals 6.28. 6.28 equals 3 plus 2t minus 0.1t cubed. By plotting the graph, theta equals 3 plus 2t minus 0.1t cubed, we can get the value or values of t for which theta equals 6.28. These are 2.11 and 3.03. There is a third negative value. When t equals 2.11, theta equals 6.28. Omega equals 2 minus 1.34, which equals 0.66 radians per second. Alpha equals negative 1.27 radians per second squared. When t equals 3.03, theta equals 6.28, omega equals 2 minus 2.754, which equals negative 0.754 radians per second. Alpha equals negative 1.82 radians per second squared. The velocity is reversed. The wheel is evidently at rest between these two instants. It is at rest when omega equals 0, that is when 0 equals 2 minus 0.3 t cubed, or when t equals 2.58 seconds. It has performed theta divided by 2 pi equals 3 plus 2 times 2.58 minus 0.1 times 2.58 cubed, all over 6.28, which equals 1.025 revolutions. End of section 13. Recording by Jargoniel.
Section 14 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Section 14. Exercises 5. 1. If y equals a plus bt squared plus ct to the fourth, find dy over dt and d2y over dt squared. Answer: dy over dt equals 2bt plus 4ct cubed. d2y over dt squared equals 2b plus 12ct squared. 2. A body falling freely in space describes in t seconds a space s in feet expressed by the equation s equals 16t squared. Draw a curve showing the relation between s and t. Also determine the velocity of the body at the following times from its being let drop. T equals 2 seconds, t equals 4.6 seconds, t equals 0.01 second. Answer: 64, 147.2, and 0.32 feet per second. 3. If x equals at minus 1/2 gt squared, find x dot and x double dot. Answer: x equals a minus gt. X double dot equals minus g. 4. If a body moves according to the law, s equals 12 minus 4.5t plus 6.2 t squared, find its velocity when t equals 4 seconds, s being in feet. Answer: 45.1 feet per second. 5. Find the acceleration of the body mentioned in the preceding example. Is the acceleration the same for all values of t? Answer: 12.4 feet per second per second. Yes. 6. The angle theta in radians, turned through by a revolving wheel, is connected with the time t in seconds that has elapsed since starting by the law theta equals 2.1 minus 3.2t plus 4.8 t squared. Find the angular velocity in radians per second of that wheel when 1 1/2 seconds have elapsed. Find also its angular acceleration. Answers: angular velocity equals 11.2 radians per second. Angular acceleration equals 9.6 radians per second per second. 7. A slider moves so that, during the first part of its motion, its distance s in inches from its starting point is given by the expression s equals 6.8 t cubed minus 10.8 t, t being in seconds. Find the expression for the velocity and the acceleration at any time. and hence find the velocity and the acceleration after 3 seconds. Answer: v equals 20.4 t squared minus 10.8. A equals 40.8 t, 172.8 inches per second, 122.4 inches per second squared. 8. The motion of a rising balloon is such that its height, h in miles, is given at any instant by the expression h equals 0.5 plus 1/10 times the cube root of t minus 125, t being in seconds. Find an expression for the velocity and the acceleration at any time. Draw curves to show the variation of height, velocity, and acceleration during the first 10 minutes of the ascent. Answers: v equals 1 over 30 times the cube root of, open parenthesis, t minus 125, close parenthesis, squared. A equals minus 1 over 45 times the cube root of, open parenthesis, t minus 125, close parenthesis, to the fifth. 9. A stone is thrown downwards into water, and its depth p in meters at any instant t seconds after reaching the surface of the water is given by the expression p equals 4 over 4 plus t squared, all plus 0.8 t minus 1. Find an expression for the velocity and the acceleration at any time. Find the velocity and acceleration after 10 seconds. Answers: v equals 0.8 minus 8t over, open parenthesis, 4 plus t squared, close parenthesis, squared. A equals 24t squared minus 32, all over, open parenthesis, 4 plus t squared, close parenthesis, cubed. 0.7926 and 0.00211. 10. A body moves in such a way that the space is described in the time t from starting is given by s equals t to the nth, where n is a constant. Find the value of n when the velocity is doubled from the 5th to the 10th second. Find it also when the velocity is numerically equal to the acceleration at the end of the 10th second. Answer: n equals 2, n equals 11. End of section 14. Section 15 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Chapter 9. Introducing a Useful Dodge. Sometimes one is stumped by finding that the expression to be differentiated is too complicated to tackle directly. Thus the equation y equals, open parenthesis, x squared plus a squared, close parenthesis, to the 3 over 2 power is awkward to a beginner. Now the dodge to turn the difficulty is this. Write some symbol, such as u, for the expression x squared plus a squared. Then the equation becomes y equals u to the 3 over 2 power, which you can easily manage. For dy over du equals 3 over 2 times u to the 1/2 power. Then tackle the expression u equals x squared plus a squared, and differentiate it with respect to x. Du over dx equals 2x. Then all that remains is plain sailing, for dy over dx equals dy over du times du over dx. That is, dy over dx equals 3 over 2 times u to the 1/2 power, all times 2x, equals 3 over 2, open parenthesis, x squared plus a squared, close parenthesis, to the 1/2 power, all times 2x, equals 3x, open parenthesis, x squared plus a squared, close parenthesis, to the 1/2 power. And so the trick is done. By and by, when you have learned how to deal with sines and cosines and exponentials, you will find this dodge of increasing usefulness. Examples. Let us practice this dodge on a few examples. 1. Differentiate y equals the square root of the quantity a plus x. Let a plus x equal u. Du over dx equals 1. Y equals u to the 1/2 power. Dy over du equals 1/2 times u to the minus 1/2 power equals 1/2 open parenthesis a plus x close parenthesis to the minus 1/2 power. Dy over dx equals dy over du times du over dx equals 1 over 2 times the square root of a plus x. 2. Differentiate y equals 1 over the square root of a plus x squared. Let a plus x squared equal u. Du over dx equals 2x. Y equals u to the minus 1/2 power. Dy over du equals minus 1/2 times u to the minus 3/2 power. Dy over dx equals dy over du times du over dx equals minus x over the square root of open parenthesis a plus x squared close parenthesis cubed. 3. Differentiate y equals open parenthesis m minus nx to the 2/3 power plus the quantity p over x to the 4/3 power close parenthesis to the power a. Let m minus nx to the 2/3 power plus px to the minus 4/3 power equal u. Du over dx equals minus 2/3 nx to the minus 1/3 power minus 4/3 px to the minus 7/3 power. Y equals u to the a power. Dy over du equals a u to the a minus 1 power. Dy over dx equals dy over du times du over dx equals minus a open parenthesis m minus nx to the 2/3 power plus p over x to the 4/3 power close parenthesis to the a minus 1 power open parenthesis 2/3 nx to the minus 1/3 power plus 4/3 px to the minus 7/3 power close parenthesis. 4. Differentiate y equals 1 over the square root of x cubed minus a squared. Let u equal x cubed minus a squared. Du over dx equals 3x squared. Y equals u to the minus 1/2. Dy over du equals minus 1/2 open parenthesis x cubed minus a squared close parenthesis to the minus 3/2. Dy over dx equals dy over du times du over dx equals minus 3x squared all over 2 times the square root of open parenthesis x cubed minus a squared close parenthesis cubed. 5. Differentiate y equals the square root of the quantity 1 minus x over 1 plus x. End quantity. Write this as y equals open parenthesis 1 minus x close parenthesis to the 1/2 all over open parenthesis 1 plus x close parenthesis to the 1/2. Dy over dx equals numerator open parenthesis 1 plus x close parenthesis to the 1/2 times the quantity numerator d open parenthesis 1 minus x close parenthesis to the 1/2 end numerator over dx end quantity minus open parenthesis 1 minus x close parenthesis to the 1/2 times the quantity numerator d open parenthesis 1 plus x close parenthesis to the 1/2 end numerator over dx, end quantity, end numerator, over denominator 1 plus x, end denominator. We may also write y equals, open parenthesis, 1 minus x, close parenthesis, to the 1/2, open parenthesis, 1 plus x, close parenthesis, to the minus 1/2, and differentiate as a product. Proceeding as in example 1 above, we get numerator d, open parenthesis, 1 minus x, close parenthesis, to the 1/2, and numerator, over denominator dx, and denominator equals minus numerator 1, and numerator, over denominator 2 times the square root of the quantity 1 minus x, and denominator, and numerator d, open parenthesis, 1 plus x, close parenthesis, to the 1/2, and numerator, over denominator dx, and denominator equals numerator 1, and numerator, over denominator 2 times the square root of the quantity 1 plus x. Hence, dy over dx equals minus numerator, open parenthesis, 1 plus x, close parenthesis, to the 1/2, and numerator, over denominator 2, open parenthesis, 1 plus x, close parenthesis, times the square root of the quantity 1 minus x, and denominator, minus numerator, open parenthesis, 1 minus x, close parenthesis, to the 1/2, and numerator, over denominator 2, open parenthesis, 1 plus x, close parenthesis, times the square root of the quantity 1 plus x, and denominator equals minus numerator 1, and numerator, over denominator 2 times the square root of the quantity 1 plus x, times the square root of the quantity 1 minus x, and denominator, minus numerator, the square root of the quantity 1 minus x, and numerator, all over denominator 2 times the square root of the quantity, open parenthesis, 1 plus x, close parenthesis, cubed, and denominator. Or dy over dx equals minus numerator 1, and numerator, over denominator, open parenthesis, 1 plus x, close parenthesis, times the square root of the quantity 1 minus x squared, and denominator. 6. Differentiate y equals the square root of the quantity x cubed over 1 plus x squared, end quantity. We may write this y equals x to the 3 over 2 power, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2. dy over dx equals 3 over 2 x to the 1/2, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2, plus x to the 3 over 2 power, times numerator d, open bracket, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2, close bracket, and numerator, over dx. Differentiating, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2, as shown in example 2 above, we get numerator d, open bracket, open parenthesis, 1 plus x squared, close parenthesis, to the minus 1/2, close bracket, and numerator, over dx, equals minus numerator x, and numerator, over denominator, the square root of, open parenthesis, 1 plus x squared, close parenthesis, cubed, and denominator. So that dy over dx equals numerator 3 times the square root of x, and numerator, over denominator 2 times the square root of the quantity 1 plus x squared, and denominator, minus numerator, the square root of x to the 5th, and numerator, over denominator, the square root of, open parenthesis, 1 plus x squared, close parenthesis, cubed, and denominator. equals numerator, the square root of x, open parenthesis, 3 plus x squared, close parenthesis, and numerator, over denominator, 2 times the square root of, open parenthesis, 1 plus x squared, close parenthesis, cubed, end denominator. 7. Differentiate y equals, open parenthesis, x plus the square root of the quantity, x squared plus x plus a, close parenthesis, cubed. Let x plus the square root of the quantity, x squared plus x plus a, equal u. Du over dx equals 1 plus numerator d, open bracket, open parenthesis, x squared plus x plus a, close parenthesis, to the 1/2, close bracket, and numerator, over dx. Y equals u cubed, and dy over du equals 3u squared, equals 3, open parenthesis, x plus the square root of the quantity, x squared plus x plus a, close parenthesis, squared. Now let, open parenthesis, x squared plus x plus a, close parenthesis, to the 1/2 equal v, and, open parenthesis, x squared plus x plus a, close parenthesis, equal w. dw over dx equals 2x plus 1. v equals w to the 1/2. dv over dw equals 1/2 w to the minus 1/2. dv over dx equals dv over dw times dw over dx equals 1/2, open parenthesis, x squared plus x plus a, close parenthesis, to the minus 1/2, open parenthesis, 2x plus 1, close parenthesis. Hence, du over dx equals 1 plus numerator 2x plus 1 and numerator over denominator 2 times the square root of the quantity x squared plus x plus a and denominator. dy over dx equals dy over du times du over dx equals 3, open parenthesis, x plus the square root of the quantity x squared plus x plus a, close parenthesis, squared, open parenthesis, 1 plus numerator 2x plus 1 and numerator over denominator 2 times the square root of the quantity x squared plus x plus a and denominator, close parenthesis. 8. Differentiate y equals the square root of the quantity, numerator a squared plus x squared, and numerator over denominator a squared minus x squared, and denominator, and quantity, times the cube root of the quantity, numerator a squared minus x squared, and numerator over denominator a squared plus x squared, and denominator, and quantity, we get y equals numerator, open parenthesis, a squared plus x squared, close parenthesis, to the 1/2, open parenthesis, a squared minus x squared, close parenthesis, to the 1/3, and numerator, over denominator, open parenthesis, a squared minus x squared, close parenthesis, to the 1/2, open parenthesis, a squared plus x squared, close parenthesis, to the 1/3, and denominator, equals, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, open parenthesis, a squared minus x squared, close parenthesis, to the minus 1/6 power. dy over dx equals, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, times numerator d, open bracket, open parenthesis, a squared minus x squared, close parenthesis, to the minus 1/6 power, close bracket, and numerator, over denominator dx, and denominator, plus numerator d, open bracket, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, close bracket, and numerator, over denominator, open parenthesis, a squared minus x squared, close parenthesis, to the 1/6 power, dx, end denominator. Let u equal, open parenthesis, a squared minus x squared, close parenthesis, to the minus 1/6, and v equal, open parenthesis, a squared minus x squared, close parenthesis. U equals v to the minus 1/6 power, du over dv equals minus 1/6 v to the minus 7/6 power. dv over dx equals minus 2x. du over dx equals du over dv times dv over dx equals 1/3 x, open parenthesis, a squared minus x squared, close parenthesis, to the minus 7/6 power. Let w equal, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, and z equal the quantity a squared plus x squared. W equals z to the 1/6 power, dw over dz equals 1/6 z to the minus 5/6 power. dz over dx equals 2x. dw over dx equals dw over dz times dz over dx equals 1/3 x, open parenthesis, a squared plus x squared, close parenthesis, to the minus 5/6 power. Hence, dy over dx equals, open parenthesis, a squared plus x squared, close parenthesis, to the 1/6 power, times numerator x and numerator over denominator 3, open parenthesis, a squared minus x squared, close parenthesis, to the 7/6 power, end denominator, plus numerator x and numerator over denominator 3, open parenthesis, a squared minus x squared, close parenthesis, to the 1/6 power, open parenthesis, a squared plus x squared, close parenthesis, to the 5/6 power, end denominator. Or dy over dx equals x over 3, open bracket, the 6th root of the quantity numerator a squared plus x squared, and numerator over denominator, open parenthesis, a squared minus x squared, close parenthesis, to the 7th power, end denominator, end quantity, end 6th root, plus 1 over denominator, the 6th root of, open parenthesis, a squared minus x squared, close parenthesis, open parenthesis, a squared plus x squared, close parenthesis, to the 5th, end 6th root, end denominator, end bracket. 9. Differentiate y to the n with respect to y to the 5th. d of y to the n over d of y to the 5th equals ny to the n minus 1 all over 5y to the 5 minus 1 equals the quantity n over 5, end quantity, times y to the n minus 5. 10. Find the first and second differential coefficients of y equals x over b times the square root of, open parenthesis, a minus x, close parenthesis, x. dy over dx equals x over b times numerator d, open brace, open bracket, open parenthesis, a minus x, close parenthesis, x, close bracket, to the 1/2, close brace, end numerator, over denominator dx, end denominator, plus numerator, the square root of, open parenthesis, a minus x, close parenthesis, x, end numerator, over denominator b, end denominator. Let, open bracket, open parenthesis, a minus x, close parenthesis, x, close bracket, to the 1/2, equal u, and let, open parenthesis, a minus x, close parenthesis, x, equal w. Then u equals w to the 1/2. du over dw equals 1/2 w to the minus 1/2 equals 1 over 2w to the 1/2 equals 1 over denominator 2 times the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator. dw over dx equals a minus 2x. du over dw times dw over dx equals du over dx equals numerator a minus 2x and numerator over denominator 2 times the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator. Hence, dy over dx equals numerator x, open parenthesis, a minus 2x, close parenthesis, and numerator over denominator 2b times the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator, plus numerator, the square root of, open parenthesis, a minus x, close parenthesis, x, and numerator, over denominator b, and denominator, equals numerator, x, open parenthesis, 3a minus 4x, close parenthesis, and numerator, over denominator 2b times the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator. Now, d2y over dx squared equals numerator 2b times the square root of, open parenthesis, a minus x, close parenthesis, x, and square root, open parenthesis, 3a minus 8x, close parenthesis, minus the quantity, numerator, open parenthesis, 3ax minus 4x squared, close parenthesis, b, open parenthesis, a minus 2x, close parenthesis, and numerator, over denominator, the square root of, open parenthesis, a minus x, close parenthesis, x, and denominator, and quantity, and numerator, all over denominator 4b squared, open parenthesis, a minus x, close parenthesis, x, and denominator, equals numerator 3a squared minus 12ax plus 8x squared, and numerator, over denominator 4b, open parenthesis, a minus x, close parenthesis, times the square root of, open parenthesis, a minus x, close parenthesis, x, and square root, and denominator. We shall need these last two differential coefficients later on. See exercise 10, number 11. End of section 15. Section 16 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bruce Kachuk. Calculus Made Easy by Silvanus P. Thompson. Section 16. Exercises 6. Differentiate the following. 1. Y equals the square root of the quantity x squared plus 1. Answer. X over the square root of the quantity x squared plus 1. 2. Y equals the square root of the quantity x squared plus a squared. Answer. X over the square root of the quantity x squared plus a squared. 3. Y equals 1 over the square root of the quantity a plus x. Answer. Minus 1 over 2 times the square root of, open parenthesis, a plus x, close parenthesis, cubed. 4. Y equals a over the square root of the quantity a minus x squared. Answer. Ax over the square root of, open parenthesis, a minus x squared, close parenthesis, cubed. 5. y equals the square root of the quantity x squared minus a squared, all over x squared. Answer: 2a squared minus x squared, all over x cubed times the square root of the quantity x squared minus a squared. 6. Y equals the cube root of the quantity x to the fourth plus a, all over the square root of the quantity x cubed plus a. Answer: numerator 3 over 2 x squared, open bracket, 8 over 9 x, open parenthesis, x cubed plus a, close parenthesis, minus, open parenthesis, x to the fourth plus a, close parenthesis, close bracket, end numerator, all over, denominator, open parenthesis, x to the fourth plus a, close parenthesis, to the 2 over 3 power, open parenthesis, x cubed plus a, close parenthesis, to the 3 over 2 power, end denominator. 7. Y equals the quantity a squared plus x squared, all over, open parenthesis, a plus x, close parenthesis, squared. Answer: 2a times the quantity x minus a, all over, open parenthesis, x plus a, close parenthesis, cubed. 8. Differentiate y to the fifth with respect to y squared. Answer: 5 over 2 y cubed. 9. Differentiate y equals the square root of the quantity 1 minus theta squared, all over 1 minus theta. Answer: 1 over the quantity 1 minus theta times the square root of the quantity 1 minus theta squared. The process can be extended to 3 or more differential coefficients, so that dy over dx equals dy over dz times dz over dv times dv over dx. Examples: 1. If z equals 3x to the fourth, v equals 7 over z squared, y equals the square root of the quantity 1 plus v, find dv over dx. We have dy over dv equals 1 over 2 times the square root of the quantity 1 plus v. dv over dz equals minus 14 over z cubed. dz over dx equals 12x cubed. dy over dx equals minus 168x cubed over, open parenthesis, 2 times the square root of the quantity 1 plus v, close parenthesis, z cubed, equals minus 28 over 3x to the fifth times the square root of the quantity 9x to the eighth plus 7. 2. If t equals 1 over 5 times the square root of theta, x equals t cubed plus the quantity t over 2, v equals 7x squared over the cube root of the quantity x minus 1, find dv over d theta. dv over dx equals 7x, open parenthesis, 5x minus 6, close parenthesis, all over 3 times the cube root of, open parenthesis, x minus 1, close parenthesis, to the fourth. dx over dt equals 3t squared plus 1/2. dt over d theta equals minus 1 over 10 times the square root of theta cubed. Hence, dv over d theta equals minus numerator 7x, open parenthesis, 5x minus 6, close parenthesis, open parenthesis, 3t squared plus 1/2, close parenthesis, end numerator, over denominator 30 times the cube root of, open parenthesis, x minus 1, close parenthesis, to the fourth, end cube root, times the square root of theta cubed, end denominator, an expression in which x must be replaced by its value, and t by its value in terms of theta. 3. If theta equals 3a squared x all over the square root of x cubed, omega equals the square root of the quantity 1 minus theta squared all over 1 plus theta, and phi equals the square root of 3 minus the quantity 1 over omega times the square root of 2. Find d phi over dx. We get theta equals 3a squared x to the minus 1/2. Omega equals the square root of the quantity 1 minus theta over 1 plus theta. And phi equals the square root of 3 minus the quantity 1 over the square root of 2 times omega to the minus 1. d theta over dx equals minus 3a squared all over 2 times the square root of x cubed. d omega over d theta equals minus 1 over the quantity 1 plus theta times the square root of 1 minus theta squared. See example 5, page 68. And d phi over d omega equals 1 over the quantity the square root of 2 times omega squared, so that d theta over dx equals 1 over the quantity the square root of 2 times omega squared, all times 1 over the quantity 1 plus theta times the square root of 1 minus theta squared, all times 3a squared over 2 times the square root of x cubed. Replace now first omega, then theta by its value. Exercises 7. You can now successfully try the following. 1. If u equals 1/2 x cubed, v equals 3 times the quantity u plus u squared, and w equals 1 over v squared, find dw over dx. Answer. dw over dx equals numerator 3x squared, open parenthesis, 3 plus 3x cubed, close parenthesis, and numerator, all over, denominator, 27, open parenthesis, 1/2 x cubed plus 1/4 x to the 6th, close parenthesis, cubed, end denominator. 2. If y equals 3x squared plus the square root of 2, z equals the square root of the quantity 1 plus y, and v equals 1 over the quantity the square root of 3 plus 4z, find dv over dx. Answer. dv over dx equals minus numerator 12x and numerator over denominator the square root of 1 plus the square root of 2 plus 3x squared, and square root, open parenthesis, the square root of 3 plus 4 times the square root of the quantity 1 plus the square root of 2 plus 3x squared, close parenthesis, squared, end denominator. 3. If y equals x cubed over the square root of 3, z equals the quantity 1 plus y squared, and u equals 1 over the square root of the quantity 1 plus z, find du over dx. Answer. du over dx equals minus numerator x squared, open parenthesis, the square root of 3 plus x cubed, close parenthesis, and numerator, all over, denominator, the square root of, open bracket, 1 plus, open parenthesis, 1 plus the quantity x cubed over the square root of 3, close parenthesis, squared, close bracket, cubed, end denominator. End of section 16.
Section 17 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson, Section 17, Chapter 10, Geometrical meaning of differentiation. Chapter 10. Geometrical meaning of differentiation. It is useful to consider what geometrical meaning can be given to the differential coefficient. In the first place, any function of x, such for example as x squared or the square root of x or ax plus b, can be plotted as a curve, and nowadays every schoolboy is familiar with the process of curve plotting. Let P, Q, and R in figure 7 be a portion of a curve plotted with respect to the axes of coordinates OX and OY. Consider any point Q on this curve, where the abscissa of the point is x and the ordinate is y. Now, observe how y changes when x is varied. If x is made to increase by a small increment, dx, to the right, it will be observed that y also, in this particular curve, increases by a small increment dy, because this particular curve happens to be an ascending curve. Then the ratio of dy to dx is a measure of the degree to which the curve is sloping up between the 2 points Q and T. As a matter of fact, it can be seen on the figure that the curve between Q and T has many different slopes, so that we cannot very well speak of the slope of the curve between Q and T. If, however, Q and T are so near each other that the small portion of QT of the curve is practically straight, then it is true to say that the ratio of dy dx is the slope of the curve along QT. The straight line QT produced on the other side touches the curve along the portion QT only, and if this portion is indefinitely small, the straight line will touch this curve at practically one point only, and be therefore a tangent to the curve. This tangent to the curve is evidently the same slope as QT, so that dy dx is the slope of the tangent to the curve at the point Q for which the value of dy dx is found. We have seen that the short expression, the slope of a curve, has no precise meaning because a curve has so many slopes. In fact, every small portion of a curve has a different slope. The slope of a curve at a point is, however, a perfectly defined thing. It is the slope of a very small portion of the curve situated just at that point, and we have seen that this is the same as the slope of the tangent to the curve at that point. Observe that dx is a short step to the right and dy the corresponding short step upwards. These steps must be considered as short as possible, in fact, indefinitely short, though in diagrams we have to represent them by bits that are not infinitesimally small, otherwise they could not be seen. We shall hereafter make considerable use of the circumstance that dy dx represents the slope of the curve at any point. If a curve is sloping up at 45 degrees at a particular point, as in figure 8, dy and dx will be equal, and the value of dy dx equals 1. If the curve slopes up steeper than 45 degrees, as in figure 9, dy dx will be greater than 1. If the curve slopes up very gently, as in figure 10, dy dx will be a fraction smaller than 1. For a horizontal line or a horizontal place in a curve, dy equals 0, and therefore dy dx equals 0. If a curve slopes downward, as in figure 11, dy will be a step down, and must therefore be reckoned of negative value, hence dy dx will have negative sign also. If the curve happens to be a straight line, like that in figure 12, the value of dy dx will be the same at all points along it. In other words, its slope is constant. If a curve is one that turns more upwards as it goes along to the right, the value of dy dx will become greater and greater with the increasing steepness, as in figure 13. If a curve is one that gets flatter and flatter as it goes along, the values of dy dx will become smaller and smaller as the flatter part is reached, as in figure 14. If a curve first descends and then goes up again, as in figure 15, presenting a concavity upwards, then clearly dy dx will first be negative, with diminishing values as the curve flattens, then will be 0 at the point where the bottom of the trough of the curve is reached, and from this point onward, dy dx will have positive values that go on increasing. In such a case, y is said to pass by a minimum. The minimum value of y is not necessarily the smallest value of y, it is that value of y corresponding to the bottom of the trough. For instance, in figure 28, The value of y corresponding to the bottom of the trough is 1, while y takes elsewhere values which are smaller than this. The characteristic of a minimum is that y must increase on either side of it. Note, for the particular value of x that makes y a minimum, the value of dy dx equals 0. If a curve first ascends and then descends, the value of dy dx will be positive at first, then 0 as the summit is reached, then negative as the curve slopes downwards as in figure 16. In this case, y is said to pass by a maximum, but the maximum value of y is not necessarily the greatest value of y. In figure 28, the maximum of y is 2 1/3, but this is by no means the greatest value of y can have at some other point of the curve. Note, for the particular value of x that makes y a maximum, the value of dy dx equals 0. If a curve has the peculiar form of figure 17, the values of dy dx will always be positive, but there will be one particular place where the slope is least steep, where the value of dy dx will be a minimum, that is, less than it is at any other part of the curve. If a curve has the form of figure 18, the value of dy dx will be negative in the upper part and positive in the lower part, while at the nose of the curve, where it becomes actually perpendicular, the value of dy dx will be infinitely great. Now that we understand that dy dx measures the steepness of a curve at any point, let us turn to some of the equations we have already learned how to differentiate. 1. As the simplest case, take this, y equals x plus b. It is plotted out in figure 19, using equal scales for x and y. If we put x equals 0, then the corresponding ordinate will be y equals b. That is to say, the curve crosses the y-axis at the height b. From here, it ascends at 45 degrees. For whatever values we give to the x to the right, we have an equal y to ascend. The line has a gradient of 1 and 1. Now differentiate y equals x plus b by the rules we have already learned, and we get dy dx equals 1. The slope of the line is such that for every little step dx to the right, we go an equal little step dy upward, and this slope is constant, always the same slope. 2. Take another case, y equals ax plus b. We know that this curve, like the preceding one, will start from a height b on the y-axis. But before we draw the curve, let us find its slope by differentiating, which gives dy dx equals a. The slope will be constant at an angle, the tangent of which is here called a. Let us assign to a some numerical value, let's say 1/3. Then we must give it such a slope that it ascends 1 3, or dx will be 3 times as great as dy, as magnified in figure 21. So, draw the line in figure 20 at this slope. 3. Now for a slightly harder case. Let y equals ax squared plus b. Again, the curve will start on the y-axis at a height b above the origin. Now differentiate. If you have forgotten, turn back to page 25, or rather don't turn back but think out the differentiation. dy dx equals 2ax. This shows that the steepness will not be constant. It increases as x increases. At the starting point P, where x equals 0, the curve of figure 22 has no steepness. That is, it is level. On the left of the origin, where x has negative values, dy dx will also have negative values, or it will descend from left to right, as in the figure. Let us illustrate this by working out a particular instance, taking the equation y equals 1/4 x squared plus 3, and differentiating it, we get dy dx equals 1/2 x. Now, assign a few successive values, say from 0 to 5 to x, and calculate the corresponding values of y by the first equation and of dy dx from the second equation. Tabulating the results, we have, for values of x, 0, 1, 2, 3, 4, 5, we have values of y of 3, 3 1/4, 4, 5 1/4, 7, 9 1/4. For values of x, 0, 1, 2, 3, 4, 5, we have dy dx equals 0, 1/2, 1, 1 1/2, 2, 2 1/2. Then plot them out in two curves, figure 23 and 24. In figure 23, plotting the value of y against those of x, and in figure 24, those of dy dx against those of x. For any assigned value of x, the height of the ordinate in the second curve is proportional to the slope of the first curve. If a curve comes to a sudden cusp, as in figure 25, the slope at that point suddenly changes from a slope upward to a slope downward. In that case, dy dx will clearly undergo an abrupt change from a positive to a negative value. The following examples will show further applications of the principles just explained. 4. Find the slope of the tangent of the curve y equals 1 over 2x plus 3 at the point where x equals minus 1. Find the angle which this tangent makes with the curve of y equals 2x squared plus 2. The slope of the tangent is the slope of the curve at the point where they touch each other. That is, it is the dy dx of the curve for that point. Here, dy dx equals minus 1 over 2x squared, and for x equals minus 1, dy dx equals minus 1/2, which is the slope of the tangent and of the curve at that point. The tangent, being a straight line, has for the equation y equals ax plus b, and its slope is dy dx equals a. Hence, a equals minus 1/2. Also, if x equals minus 1, y equals 1 over 2 times minus 1 plus 3, and that equals 2.5. And as the tangent passes by this point, the coordinates of the point must satisfy the equation of the tangent, namely y equals minus 1/2 x plus b, so that 2.5 equals minus half times minus 1 plus b, and b equals 2. The equation of the tangent is therefore y equals minus half x plus 2. Now when the two curves meet, the intersection being a point common to both curves, its coordinates must satisfy the equation of each one of the two curves. That is, it must be a solution of the system of simultaneous equations formed by coupling together the equations of the curves. Here, the curves meet one another at points given by the solution of y equals 2x squared plus 2 and y equals minus 1/2 x plus 2, or 2x squared plus 2 equals minus 1/2 x plus 2. That is, x times the quantity of 2x plus 1/2 equals 0. This equation has for its solution x equals 0 and x equals minus 1/4. The slope of the curve y equals 2x squared plus 2 at any point is dy dx equals 4x. For the point where x equals 0, the slope is 0. The curve is horizontal. For the point where x equals minus 1/4, dy dx equals minus 1. Hence the curve at the point slopes downward to the right at such an angle theta with the horizontal that tan theta equals 1. That is, at 45 degrees to the horizontal. The slope of the straight line is minus 1/2. That is, it slopes downwards to the right and makes with the horizontal an angle phi such that tan phi equals 1/2. That is an angle of 26 degrees 34 minutes. It follows that at the first point the curve cuts the straight line at an angle of 26 degrees 34 minutes, while at the second it cuts at an angle of 45 degrees minus 26 degrees 34 minutes, which equals 18 degrees 26 minutes. 5. A straight line is to be drawn through a point whose coordinates are x equal 2 and y equals minus 1. As tangent to the curve, y equals x squared minus 5x plus 6. Find the coordinates of the point of contact. The slope of the tangent must be the same as dy dx of the curve, that is, 2x minus 5. The equation of the straight line is y equals ax plus b, and it is satisfied for the values of x equals 2 and y equals minus 1. Then minus 1 equals a times 2 plus b. Also, its dy dx equals a equals 2x minus 5. The x and the y of the point of contact must also satisfy both the equations of the tangent and the equations of the curve. We have then simultaneous equations y equals x squared minus 5x plus 6, y equals ax plus b, minus 1 equals 2a plus b, and a equals 2x minus 5. four equations in a, b, x, y. Equations 1 and 2 give us x squared minus 5x plus 6 equals ax plus b. Replacing a and b by their values in this, we get x squared minus 5x plus 6 equals the quantity 2x minus 5 times x minus 1 minus 2 times the quantity 2x minus 5, which simplifies to x squared minus 4x plus 3 equals 0, the solutions of which are x equals 3 and x equals 1. Replacing in equation 1, we get y equals 0 and y equals 2, respectively. The 2 points of contact are then x equal 1, y equal 2, and x equal 3, y equals 0. Note, in all exercises dealing with curves, students will find it extremely instructive to verify the deductions obtained by actually plotting the curves. End of section 17.
Section 18 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 18. Exercises 8. 1. Plot the curve y equals 3/4 x squared minus 5 using a scale of millimeters. Measure at points corresponding to different values of x the angle of its slope. Find, by differentiating the equation, the expression for slope, and see, from a table of natural tangents, whether this agrees with the measured angle. 2. Find what will be the slope of the curve y equals 0.12x cubed minus 2 at the particular point that has an abscissa x equal 2. Answer: 1.44. 3. If y equal the quantity x minus a times the quantity x minus b, show that at the particular point of the curve where dy over dx equals 0, x will have the value 1/2 times the quantity a plus b. 4. Find the dy over dx of the equation y equals x cubed plus 3x and calculate the numerical values of dy over dx for the points corresponding to x equals 0, x equal 1/2, x equal 1, x equal 2. Answer: dy over dx equal 3x squared plus 3, and the numerical values are 3, 3 3/4, 6, and 15. 5. In the curve to which the equation is x squared plus y squared equal 4, find the values of x at those points where the slope equal 1. Answer: plus or minus the square root of 2. 6. Find the slope, at any point, of the curve whose equation is x squared over 3 squared plus y squared over 2 squared equal 1, and give the numerical value of the slope at the place where x equals 0, and at that where x equal 1. Answer: dy over dx equal -4/9 times x over y. Slope is 0 where x equals 0, and it is plus or minus 1/3 times the square root of 2, where x equal 1. 7. The equation of a tangent to the curve y equal 5 minus 2x plus 0.5 x cubed, being of the form y equal mx plus n, where m and n are constants, find the value of m and n if the point where the tangent touches the curve has x equal 2 for abscissa, Answer: m equal 4, n equal -3. 8. At what angles do the two curves y equal 3.5 x squared plus 2 and y equal x squared minus 5x plus 9.5 cut one another? Answer: intersections at x equal 1, x equal -3, angles 153 degrees 26 minutes, 2 degrees 28 minutes. 9. Tangents to the curve y equal plus or minus the square root of 25 minus x squared are drawn at points for which x equal 3 and x equal 4. Find the coordinates of the points of intersection of the tangents and their mutual inclination. Answer: intersection at x equal 3.57, y equal 3.50, angle 16 degrees 16 minutes. 10. A straight line, y equal 2x minus b, touches a curve y equal 3x squared plus 2 at one point. What are the coordinates of the point of contact, and what is the value of b? Answer: x equal 1/3, y equal 2 1/3, b equal -5/3. End of section 18.
Section 19 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 11. Maxima and Minima, Part 1. One of the principal uses of the process of differentiating is to find out under what conditions the value of the thing differentiated becomes a maximum or a minimum. This is often exceedingly important in engineering questions, where it is most desirable to know what conditions will make the cost of working a minimum or will make the efficiency a maximum. Now, to begin with a concrete case, let us take the equation y equals x squared minus 4x plus 7. By assigning a number of successive values to x and finding the corresponding values of y, we can readily see that the equation represents a curve with a minimum. When x equals 0, y equals 7. When x equals 1, y equals 4. When x equals 2, y equals 3. When x equals 3, y equals 4. When x equals 4, y equals 7. When x equals 5, y equals 12. These values are plotted in Figure 26, which shows that y has apparently a minimum value of 3 when x is made equal to 2. But are you sure that the minimum occurs at 2 and not in 2 1/4 or 1 3/4? Note: Figure 26 shows a graph with the curve y equals x squared minus 4x plus 7, plotted with dotted lines indicating the earlier mentioned points. Of course, it would be possible with any algebraic expression to work out a lot of values, and in this way arrive gradually at the particular value that may be a maximum or a minimum. Here is another example. Let y equals 3x minus x squared. Calculate a few values thus. When x equals minus 1, y equals minus 4. When x equals 0, y equals 0. When x equals 1, y equals 2. When x equals 2, y equals 2. When x equals 3, y equals 0. When x equals 4, y equals minus 4. When x equals 5, y equals minus 10. Plot these values as in figure 27. Note: figure 27 shows the curve y equals 3x minus x squared plotted with dotted lines indicating previously mentioned points. The maximum value is somewhere between 1 and 2 on the x-axis. It will be evident that there will be a maximum somewhere between x equals 1 and x equals 2, and the thing looks as if the maximum value of y ought to be about 2 1/4. Try some intermediate values. If x equals 1 1/4, y equals 2.187. If x equals 1 1/2, y equals 2.25. If x equals 1.6, y equals 2.24. How can we be sure that 2.25 is the real maximum, or that it occurs exactly when x equals 1 1/2? Now, it may sound like juggling to be assured that there is a way by which one can arrive straight at a maximum or minimum value without making a lot of preliminary trials or guesses, and that way depends on differentiating. Look back to an earlier page, 78, for the remarks about figures 14 and 15, and you will see that whenever a curve gets either to its maximum or to its minimum height, at that point its dy over dx equals 0. Now this gives us the clue to the dodge that is wanted. When there is put before you an equation, and you want to find that value of x which will make its y a minimum or a maximum, first differentiate it, and having done so, write its dy over dx as equal to 0, and then solve for x. Put this particular value of x into the original equation, and you will then get the required value of y. This process is commonly called equating to 0. To see how simply it works, take the example with which this chapter opens, namely y equals x squared minus 4x plus 7. Differentiating, we get dy over dx equals 2x minus 4. Now equate this to 0, thus 2x minus 4 equals 0. Solving this equation for x, we get 2x equals 4, x equals 2. Now we know that the maximum or minimum will occur exactly when x equals 2. Putting the value x equals 2 into the original equation, we get y equals 2 squared minus 4 times 2 plus 7 equals 4 minus 8 plus 7 equals 3. Now look back at figure 26, and you will see that the minimum occurs when x equals 2, and that this minimum of y equals 3. Try the second example, figure 27, which is y equals 3x minus x squared. Differentiating, dy over dx equals 3 minus 2x, equating to 0. 3 minus 2x equals 0, whence x equals 1 1/2. And putting this value of x into the original equation, we find y equals 4 1/2 minus 1 1/2 times 1 1/2, y equals 2 1/4. This gives us exactly the information as to which the method of trying a lot of values left us uncertain. Now before we go on to any further cases, we have two remarks to make. When you are told to equate dy over dx to 0, you feel at first, that is if you have any wits of your own, a kind of resentment, because you know that dy over dx has all sorts of different values at different parts of the curve, according to whether it is sloping up or down. So when you are suddenly told to write dy over dx equals 0, you resent it, and feel inclined to say that it can't be true. Now you will have to understand the essential difference between an equation and an equation of condition. Ordinarily, you are dealing with equations that are true in themselves, but, on occasions, of which the present are examples, you have to write down equations that are not necessarily true, but are only true if certain conditions are to be fulfilled, and you write them down in order, by solving them, to find the conditions which make them true. Now we want to find the particular value that $x$ has when the curve is neither sloping up nor sloping down, that is, at the particular place where dy/dx equals 0. So, writing dy/dx equals 0 does not mean that it is always equal 0, but you write it down as a condition in order to see how much x will come out if dy/dx is to be 0. The second remark is one which, if you have any wits of your own, you will probably have already made, namely, that this much belauded process of equating to 0 entirely fails to tell you whether the x that you thereby find is going to give you a maximum value of y or a minimum value of y. Quite so. It does not of itself discriminate. It finds for you the right value of x, but leaves you to find out for yourselves whether the corresponding y is a maximum or a minimum. Of course, if you have plotted the curve, you know already which it will be. For instance, take the equation y equals 4x plus 1 over x. Without stopping to think what curve it corresponds to, differentiate it and equate to 0. dy/dx equals 4 minus x to the power of minus 2 equals 4 minus 1 over x squared equals 0, whence x equals a half, and inserting this value, y equals 4, will be either a maximum or else a minimum, but which? You will hereafter be told away, depending upon a second differentiation. But at present it is enough if you will simply try any other value of x differing a little from the one found, and see whether with this altered value the corresponding value of y is less or greater than that already found. Try another simple problem in maxima and minima. Suppose you were asked to divide any number into two parts, such that the product was a maximum. How would you set about it if you did not know the trick of equating to 0? I suppose you could worry it out by the rule of try, try, try again. Let 60 to be the number. You can try cutting it into two parts and multiplying them together. Thus 50 times 10 is 500, 52 times 8 is 416, 40 times 20 is 800, 45 times 15 is 675, 30 times 30 is 900. This looks like a maximum. Try varying it. 31 times 29 is 899, which is not so good, and 32 times 28 is 896, which is worse. So it seems that the biggest product will be got by dividing into two equal halves. Now see what the calculus tells you. Let the number to be cut into two parts be called n. Then if x is one part, the other will be n minus x, and the product will be x (open brackets) n minus x close brackets, or nx minus x squared. So we write y equals nx minus x squared. Now differentiate and equal to 0. dy/dx equals n minus 2x equals 0. Solving for x, we get n over 2 equals x. So now we know that whatever number n may be, we must divide it into two equal parts if the product of the parts is to be a maximum, and the value of that maximum product will always be equal 1/4 n squared. This is a very useful rule, and applies to any number of factors, so that if m plus n plus p equals a constant number, n times p is a maximum when m equals n equals p. Test case. Let us at once apply our knowledge to a case that we can test. Let y equal x squared minus x, and let us find whether this function has a maximum or minimum, and if so, test whether it is a maximum or a minimum. Differentiating, we get dy/dx equals 2x minus 1. Equating to 0, we get 2x minus 1 equals 0, whence 2x equals 1, or x equals 1/2. That is to say, when x is made equal 1/2, the corresponding value of y will either be a maximum or a minimum. Accordingly, putting x equals 1/2 in the original equation, we get y equals 1/2 squared minus 1/2, or y equals minus a quarter. Is this a maximum or a minimum? To test it, try putting x a little bigger than half, say make x equal 0.6, then y equals 0.6 squared minus 0.6 equals 0.36 minus 0.6 equals minus 0.24, which is higher up than minus 0.25, showing that y equals 0.25 is a minimum. Plot the curve for yourself and verify the calculation. End of section 19. Section 20 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 11, Maxima and Minima, Part 2. Further examples. A most interesting example is afforded by a curve that has both a maximum and a minimum. Its equation is y equals 1/3 x cubed minus 2x squared plus 3x plus 1. Now, dy over dx equals x squared minus 4x plus 3. Equating to 0, we get the quadratic x squared minus 4x plus 3 equals 0, and solving the quadratic gives us two roots, viz. X equals 3 and x equals 1. Now, when x equals 3, y equals 1, and when x equals 1, y equals 2 1/3. The first of these is a minimum, the second a maximum. The curve itself may be plotted from the values calculated as below from the original equation. When x equals minus 1, y equals minus 4 1/3. When x equals 0, y equals 1. When x equals 1, y equals 2 1/3. When x equals 2, y equals 1 2/3. When x equals 3, y equals 1. When x equals 4, y equals 2 1/3. When x equals 5, y equals 7 2/3. When x equals 6, y equals 19. A further exercise in maxima and minima is afforded by the following example. The equation to a circle of radius r, having its centre C at the point whose coordinates are x equals a, y equals b, as depicted in figure 29 is open brackets y minus b close brackets squared plus open brackets x minus a close brackets squared equals r squared. Note: figure 29 shows a circle in the xy plane as described, with a line from the centre of the circle to the edge labelled r for the radius. This may be transformed into y equals the square root of r squared minus open brackets x minus a close brackets squared and plus b. Now we know beforehand, by mere inspection of the figure, that when x equals a, y will be either at its maximum value b plus r, or else its minimum value b minus r. But let us not take advantage of this knowledge. Let us set about finding what value of x will make y a maximum or a minimum by the process of differentiating and equating to 0. dy over dx equals 1/2 times 1 over the square root of r squared minus open brackets x minus a close brackets squared times by open brackets 2a minus 2x close brackets, which reduces to dy over dx equals a minus x all over square root of r squared minus open brackets x minus a close brackets squared. Then the condition for y being maximum or minimum is a minus x all over the square root of r squared minus open brackets x minus a close brackets squared equals 0. Since no value whatever of x will make the denominator infinite, the only condition to give 0 is x equals a. Inserting this value in the original equation for the circle, we find y equals square root of r squared plus b. And as the root of r squared is either plus r or minus r, we have two resulting values of y equals b plus r, y equals b minus r. The first of these is the maximum at the top, the second is the minimum at the bottom. If the curve is such that there is no place that is a maximum or a minimum, the process of equating to 0 will yield an impossible result. For instance, let y equals ax cubed plus bx plus c, then dy over dx equals 3ax squared plus b. Equating this to 0, we get 3ax squared plus b equals 0. X squared equals minus b over 3a, and x equals the square root of minus b over 3a, which is impossible. Therefore y has no maximum nor minimum. A few more worked examples will enable you to thoroughly master this most interesting and useful application of the calculus. 1. What are the sides of the rectangle of maximum area inscribed in a circle of radius r? If one side be called x, the other side equals the square root of diagonal squared minus x squared. And as the diagonal of the rectangle is necessarily a diameter, the other side equals square root of 4r squared minus x squared. Then area of rectangle S equals x times the square root of 4r squared minus x squared. ds over dx equals x times d open brackets square root of 4r squared minus x squared close brackets over dx plus the square root of 4r squared minus x squared times dx over dx. If you have forgotten how to differentiate the square root of 4r squared minus x squared, here is a hint. Write 4r squared minus x squared equals w, and y equals the square root of w, and seek dy over dw and dw over dx. Fight it out, and only if you can't get on refer to page 66. You will get ds over dx equals x times minus x over square root of 4r squared minus x squared, add the square root of 4r squared minus x squared, equals 4r squared minus 2x squared all over the square root of 4r squared minus x squared. For maximum or minimum, we must have 4r squared minus 2x squared all over the square root of 4r squared minus x squared equals 0. That is, 4r squared minus 2x squared equals 0, and x equals r times root 2. The other side equals square root of 4r squared minus 2r squared equals r times the square root of 2. The two sides are equal. The figure is a square, the side of which is equal to the diagonal of the square constructed on the radius. In this case, of course, it is a maximum with which we are dealing. 2. What is the radius of the opening of a conical vessel, the sloping side of which has a length L when the capacity of the vessel is greatest? If r be the radius and h the corresponding height, h equals the square root of L squared minus r squared. Volume V equals pi r squared times h over 3 equals pi r squared times the square root of L squared minus r squared all over 3. Proceeding as in the previous problem, we get dv over dr equals pi r squared times minus r over 3 times the square root of L squared minus r squared plus 2 pi r over 3 times the square root of L squared minus r squared equals 2 pi r open brackets L squared minus R squared close brackets minus pi r cubed all over 3 times the square root of L squared minus R squared equals 0 for maximum or minimum, or 2 pi r open brackets L squared minus R squared close brackets minus pi r cubed equals 0, and r equals L times the square root of 2 over 3 for a maximum, obviously. 3. Find the maxima and minima of the function y equals x over 4 minus x plus 4 minus x all over x. We get dy over dx equals open brackets 4 minus x close brackets minus open brackets minus x close brackets all over open brackets 4 minus x close brackets squared plus minus x minus open brackets 4 minus x close brackets all over x squared equals 0. The maximum or minimum, or 4 over open brackets 4 minus x close brackets squared minus 4 over x squared equals 0, and x equals 2. There is only one value, hence only one maximum or minimum. For x equals 2, y equals 2. For x equals 1.5, y equals 2.27. For x equals 2.5, y equals 2.27. It is therefore a minimum. It is instructive to plot the graph of the function. 4. Find the maxima and minima of the function y equals the square root of 1 plus x add the square root of 1 minus x. It will be found instructive to plot the graph. Differentiating gives at once. See example number 1, page 67. dy over dx equals 1 over 2 times the square root of 1 add x minus 1 over 2 times the square root of 1 minus x equals 0 for maximum or minimum. Hence, square root of 1 plus x equals the square root of 1 minus x, and x equals 0 the only solution. For x equals 0, y equals 2. For x equals plus minus 0.5, y equals 1.932, so it is a maximum. 5. Find the maxima and minima of the function y equals x squared minus 5 all over 2x minus 4. We have dy over dx equals open brackets 2x minus 4 close brackets times 2x minus open brackets x squared minus 5 close brackets times 2 all over open brackets 2x minus 4 close brackets squared equals 0. The maximum or minimum, or 2x squared minus 8x plus 10 all over open brackets 2x minus 4 close brackets squared equals 0, or x squared minus 4x plus 5 equals 0, which has for solutions x equals 5 over 2 plus minus square root of minus 1. These being imaginary, there is no real value of x for which dy over dx equals 0, hence there is neither maximum nor minimum. 6. Find the maxima and minima of the function open brackets y minus x squared close brackets squared equals x to the power 5. This may be written y equals x squared plus minus x to the power of 5 over 2. dy over dx equals 2x plus minus 5 over 2 times x to the power of 3 over 2 equals 0 for maximum or minimum. That is, x open brackets 2 plus minus 5 over 2 times x to the power of 1 over 2 close brackets equals 0, which is satisfied for x equals 0, and for 2 plus minus 5 over 2 x to the power of a half equals 0, that is, for x equals 16 over 25. So there are two solutions. Taking first x equals 0, If x equals minus 0.5, y equals 0.25 plus minus the square root of minus 0.5 to the power of 5, and if x equals plus 0.5, y equals 0.25 plus minus square root of 0.5 to the power of 5. On the one side, y is imaginary, that is, there is no value of y that can be represented by a graph. The latter is therefore entirely on the right side of the axis of y. See Figure 30. On plotting the graph, it will be found that the curve goes to the origin as if there were a minimum there, but instead of continuing beyond, as it should do for a minimum, it retraces its steps, forming what is called a cusp. There is no minimum, therefore, although the condition for a minimum is satisfied, namely dy over dx equals 0. It is necessary, therefore, always to check by taking one value on either side. Now, if we take x equals 16 over 25 equals 0.64, if x equals 0.64, y equals 0.7373, and y equals 0.0819, if x equals 0.6, y becomes 0.6389 and 0.0811, and if x equals 0.7, y becomes 0.8996 and 0.0804. This shows that there are two branches of the curve. The upper one does not pass through a maximum, but the lower one does. 7. A cylinder whose height is twice the radius of the base is increasing in volume, so that all its parts keep always in the same proportion to each other, that is, at any instant the cylinder is similar to the original cylinder. When the radius of the base is r feet, the surface area is increasing at the rate of 20 square inches per second. At what rate is its volume then increasing? Area equals S equals 2 times pi r squared plus 2 pi r times 2r equals 6 pi r squared. Volume equals V equals pi r squared times 2r equals 2 pi r cubed. ds over dr equals 12 pi r, dv over dr equals 6 pi r squared. ds equals 12 pi r dr equals 20, dr equals 20 over 12 pi r, dv equals 6 pi r squared dr equals 6 pi r squared times 20 over 12 pi r equals 10r. The volume changes at the rate of 10 r cubic inches. Make other examples for yourself. There are few subjects which offer such a wealth for interesting examples. End of section 20. Section 21 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 21. Exercises 9. 1. What values of x will make y a maximum and a minimum if y equals x squared over x plus 1? Answer. Minimum, x equals 0, y equals 0. Maximum, x equals minus 2, y equals minus 4. 2. What value of x will make y a maximum in the equation? Y equals x over a squared plus x squared. Answer. X equals a. 3. A line of length p is to be cut up into 4 parts and put together as a rectangle. Show that the area of the rectangle will be a maximum if each of its sides is equal to 1/4 p. 4. A piece of string 30 inches long has its two ends joined together and is stretched by 3 pegs so as to form a triangle. What is the largest triangular area that can be enclosed by the string? Answer: 25√3 square inches. 5. Plot the curve corresponding to the equation y equals 10 over x add 10 over 8 minus x. Also find dy over dx and deduce the value of x that will make y a minimum and find that minimum value of y. Answer: dy over dx equals minus 10 over x squared add 10 over open brackets 8 minus x close brackets squared. Minimum: x equals 4, y equals 5. 6. If y equals x to the power 5 minus 5x, find what values of x will make y a maximum or a minimum. Answer: max for x equals minus 1, min for x equals 1. 7. What is the smallest square that can be inscribed in a given square? Answer: join the middle points of the four sides. 8. Inscribe in a given cone, the height of which is equal to the radius of the base, a cylinder A, whose volume is a maximum, B, whose lateral area is a maximum, C, whose total area is a maximum. Answer: A, radius equals 2 over 3r, B, radius equals r over 2, C, no max. 9. Inscribe in a sphere a cylinder A, whose volume is a maximum, B, whose lateral area is a maximum, C, whose total area is a maximum. Answer: A, radius equals r root 2/3, B, radius equals r over root 2, C, radius equals 0.8506 r. 10. A spherical balloon is increasing in volume if, when its radius is r feet, its volume is increasing at a rate of 4 cubic feet per second. At what rate is its surface then increasing? Answer: at a rate of 8 over r square feet per second. 11. Inscribe in a given sphere a cone whose volume is a maximum. Answer: radius equals r root 8 over 3. 12. The current C, given by a battery of big N similar voltic cells, is C equals little n times E all over big R plus little r little n squared over big N, where E, big R, little r are constants and little n is the number of cells coupled in series. Find the proportion of little n to big N, for which the current is greatest. Answer: little n equals root big N, big R over little r. End of section 21. Section 22 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 12. Curvature of Curves. Returning to the process of successive differentiation, it may be asked, why does anybody want to differentiate twice over? We know that when the variable quantities are space and time, by differentiating twice over we get the acceleration of a moving body, and that in the geometrical interpretation, as applied to curves, dy over dx means the slope of the curve, but what can d2y over dx squared mean in this case? Clearly it means the rate, per unit length of x, at which the slope is changing. In brief, it is a measure of the curvature of the slope. Suppose a slope constant, as in figure 31. Note: Figure 31 shows a graph of a straight positive line with evenly spaced rectangles going up the line underneath. Here, dy over dx is of constant value. Suppose, however, a case in which, like figure 32, the slope itself is getting greater upwards than d open brackets dy over dx close brackets over dx, that is, d2y over dx squared will be positive. Note: Figure 32 shows a positively curved, positive line with evenly spaced rectangles underneath. As the line is curved, the difference in height is increasing for each subsequent rectangle. If the slope is becoming less as you go to the right, as in figure 33, then, even though the curve may be going upward, since the change is such as to diminish its slope, its d2y over dx squared will be negative. Note: Figure 33 shows a negatively curved positive line with the same even rectangles. As it is negatively curved, the difference in height is decreasing for the rectangles. It is now time to initiate you into another secret: how to tell whether the result that you get by equating to zero is a maximum or a minimum. The trick is this: after you have differentiated, so as to get the expression which you equate to zero, you then differentiate a second time and look whether the result of the second differentiation is positive or negative. If d2y over dx squared comes out positive, then you know that the value of y which you got was a minimum, but if d2y over dx squared comes out negative, then the value of y which you got out must be a maximum. That's the rule. The reason of it ought to be quite evident. Think of any curve that has a minimum point in it, like figure 34, where the point of minimum y is marked M and the curve is concave upwards. Note: Figure 34 shows a curve with a minimum labelled M. Before the minimum there is a downward pointing arrow, and after it there is an upward pointing arrow. To the left of M the slope is downward, that is, negative, and is getting less negative. To the right of M the slope has become upward and is getting more and more upward. Clearly the change of slope, as the curve passes through M, is such that d2y over dx squared is positive, for its operation, as x increases toward the right, is to convert a downward slope into an upward one. Similarly, consider any curve that has a maximum point in it, like figure 35, where the curve is convex and the maximum point is marked M. Note: 35 shows a curve with a maximum labelled M. Before the maximum there is an upward pointing arrow, and after it there is a downward pointing arrow. In this case, as the curve passes through M from left to right, its upward slope is converted into a downward or negative slope, so that in this case the slope of the slope, d2y over dx squared, is negative. Go back now to the examples of the last chapter and verify in this way the conclusions arrived at as to whether in any particular case there is a maximum or a minimum. You'll find below a few worked out examples. 1. Find the maximum or minimum of a. y equals 4x squared minus 9x minus 6. b. y equals 6 add 9x minus 4x squared. And ascertain if it will be a maximum or a minimum in each case. A. dy over dx equals 8x minus 9 equals 0, x equals 1 and an eighth, and y equals minus 11.065. d2y over dx squared equals 8. It is positive, hence it is a minimum. B. dy over dx equals 9 minus 8x equals 0, x equals 1/8, and y equals 11.065. d2y over dx squared equals minus 8. It is negative, hence it is a maximum. 2. Find the maxima and minima of the function y equals x cubed minus 3x plus 16. dy over dx equals 3x squared minus 3 equals 0. X squared equals 1 and x equals plus minus 1. d2y over dx squared equals 6x. For x equals 1 it is positive. Hence x equals 1 corresponds to a minimum, y equals 14. For x equals minus 1 it is negative. Hence x equals minus 1 corresponds to a maximum, y equals 18. 3. Find the maxima and minima of y equals x minus 1 all over x squared plus 2. dy over dx equals open brackets x squared plus 2 close brackets times 1 minus open brackets x minus 1 close brackets times 2x all over open brackets x squared plus 2 close brackets squared equals 2x minus x squared plus 2 all over open brackets x squared plus 2 close brackets squared equals 0, or x squared minus 2x minus 2 equals 0, whose solutions are x equals 2.73 and x equals minus 0.73. d2y over dx squared equals minus open brackets x squared plus 2 close brackets squared times open brackets 2x minus 2 close brackets minus open brackets x squared minus 2x minus 2 close brackets open brackets 4x cubed plus 8x close brackets all over open brackets x squared plus 2 close brackets to the power of 4 equals minus 2x to the power of 5 minus 6x to the power of 4 minus 8x cubed minus 8x squared minus 24x plus 8 all over open brackets x squared plus 2 close brackets to the power of 4. The denominator is always positive, so it is sufficient to ascertain the sign of the numerator. If we put x equals 2.73, the numerator is negative, the maximum y equals 0.183. If we put x equals minus 0.73, the numerator is positive, the minimum y equals minus 0.683. 4. The expense C of handling the products in a certain factory varies with the weekly output P according to the relation C equals AP add B over C add P add D, where A, B, C, D are positive constants. For output will the expense be least. dC over dP equals A minus B over open brackets C add P close brackets squared equals 0 for maximum or minimum. Hence A equals B over open brackets C add P close brackets squared, and P equals plus minus square root of B over A minus C. As the output cannot be negative, P equals positive square root of B over A minus C. Now, d2c over dp squared equals b open brackets 2c add 2p close brackets all over open brackets c add p close brackets to the power of 4, which is positive for all the values of p, hence p equals positive square root b over a minus c corresponds to a minimum. 5. The total cost per hour C of lighting a building with n lamps of a certain kind is C equals n open brackets CL over T add EPCE over 1000 close brackets, where E is the commercial efficiency, watts per candle, P is the candle power of each lamp, T is the average life of each lamp in hours, CL the cost of renewal in pence per hour of use, CE the cost of energy per 1000 watts per hour. Moreover, the relation connecting the average life of a lamp with the commercial efficiency at which it is run is approximately T equals m(e) to the power of little n, where m and little n are constants depending on the kind of lamp. Find the commercial efficiency for which the total cost of lighting will be least. We have C equals n open brackets CL e to the power of minus little n over m add PCE e over 1000 close brackets. DC over DE equals PCE over 1000 minus little n CL e to the power of minus open brackets little n plus 1 close brackets over m equals 0 for maximum or minimum. E to the power of little n plus 1 equals 1000 times little n CL over MPCE, and E equals root to the little n plus 1 1000 times little n CL over MPCE. This is clearly for minimum, since d2c over de squared equals open brackets little n add 1 close brackets little n CL e to the power of minus open brackets little n add 2 close brackets over m, which is positive for a positive value of E. For a particular type of 16 candle power lamps, CL equals 17 pence, CE equals 5 pence, and it was found that m equals 10 and little n equals 3.6. E equals root to the 4.6 1000 times 3.6 times 17 over 10 times 16 times 5 equals 2.6 watts per candle power. End of section 22. Section 23 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Section 23. Exercises 10. You are advised to plot the graph of any numerical example. 1. Find the maxima and minima of y equals x cubed plus x squared minus 10x plus 8. Answer. Max, x equals minus 2.19, y equals 24.19. Min, x equals 1.52, y equals minus 1.38. 2. Given y equals b over a x minus c x squared, find expressions for dy over dx and for d2y over dx squared. Also find the value of x which makes y a maximum or a minimum, and show whether it is maximum or minimum. Answer. dy over dx equals b over a minus 2cx. d2y over dx squared equals minus 2c. X equals b over 2ac, a maximum. 3. Find how many maxima and how many minima there are in the curve, the equation to which is y equals 1 minus x squared over 2 plus x to the power of 4 over 24, and how many in that of which the equation is y equals 1 minus x squared over 2, add x to the power of 4 over 24, minus x to the power of 6 over 720. Answers: A, 1 maximum and 2 minima. B, 1 maximum, x equals 0, other points unreal. 4. Find the maxima and minima of y equals 2x add 1 add 5 over x squared. Answer: min x equals 1.71, y equals 6.14. 5. Find the maxima and minima of y equals 3 over x squared plus x plus 1. Answer: max x equals minus 0.5, y equals 4. 6. Find the maxima and minima of y equals 5x over 2 and x squared. Answer: max x equals 1.414, y equals 1.7675. Min x equals minus 1.414, y equals 1.7675. 7. Find the maxima and minima of y equals 3x over x squared minus 3, add x over 2, add 5. Answer: max x equals minus 3.565, y equals 2.12. Min x equals 3.565, y equals 7.88. 8. Divide a number n into two parts in such a way that 3 times the square of one part plus twice the square of the other part shall be a minimum. Answer: 0.4n, 0.6n. 9. The efficiency U of an electric generator at different values of output x is expressed by the general equation U equals x over a plus bx plus cx squared, where a is a constant depending chiefly on the energy losses in the iron, and c a constant depending chiefly on the resistance of the copper parts. Find an expression for that value of the output for which the efficiency will be a maximum. Answer: x equals root a over c. 10. Suppose it to be known that consumption of coal by a certain steamer may be represented by the formula y equals 0.3 add 0.001 v cubed, where y is the number of tons of coal burned per hour, and v is the speed expressed in nautical miles per hour. The cost of wages, interest on capital, and depreciation of that ship are together equal, per hour, to the cost of 1 ton of coal. What speed will make the total cost of a voyage of 1000 nautical miles a minimum? And, if coal costs 10 shillings per ton, what will that minimum cost of the voyage amount to? Answer: speed 8.66 nautical miles per hour, time taken 115.47 hours, minimum cost £112 and 12 shillings. 11. Find the maxima and minima of y equals plus minus x over 6 square root of x open brackets 10 minus x closed brackets. Answer: max and min for x equals 7.5, y equals plus minus 5.414. 12. Find the maxima and minima of y equals 4x cubed minus x squared minus 2x plus 1. Answer. Min x equals a half, y equals 0.25. Max x equals minus a third, y equals 1.408. End of section 23. Section 24 of Calculus Made Easy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Calculus Made Easy by Silvanus P. Thompson. Chapter 13 of the Useful Dodges, Part 1. Partial Fractions. We have seen that when we differentiate a fraction we have to perform a rather complicated operation and, if the fraction is not itself a simple one, the result is bound to be a complicated expression. If we could split the fraction into two or more simpler fractions, such that their sum is equivalent to the original fraction, we could then proceed by differentiating each of these simpler expressions, and the result of differentiating would be the sum of two or more differentials, each one of which is relatively simple, while the final expression, though of course it will be the same as that which could be attained without resorting to this dodge, is thus obtained with much less effort and appears in a simplified form. Let us see how to reach this result. Try first the job of adding two fractions together to form a resultant fraction. Take, for example, the two fractions 1 over x add 1 and 2 over x minus 1. Every schoolboy can add these together and find their sum to be 3x add 1 all over x squared minus 1. And in the same way he can add together three or more fractions. Now this process can certainly be reversed, that is to say, that if this last expression were given, it is certain that it can somehow be split back again into its original components or partial fractions. Only we do not know in every case that may be presented to us how we can so split it. In order to find this out we shall consider a simple case at first, but it is important to bear in mind that all which follows applies only to what are called proper algebraic fractions, meaning fractions like the above, which have the numerator of a lesser degree than the denominator, that is, those in which the highest index of x is less in the numerator than in the denominator. If we have to deal with such an expression as x squared add 2 all over x squared minus 1, we can simplify it by division, since it is equivalent to 1 add 3 over x squared minus 1, and 3 over x squared minus 1 is a proper algebraic fraction to which the operation of splitting into partial fractions can be applied, as explained hereafter. Case 1. If we perform many additions of two or more fractions, the denominators of which contain only terms in x and no terms in x squared, x cubed, or any other powers of x, we always find that the denominator of the final resulting fraction is the product of the denominators of the fractions which were added to form the result. It follows that by factorising the denominator of this final fraction, we can find every one of the denominators of the partial fractions of which we are in search. Suppose we wish to go back from 3x add 1 all over x squared minus 1 to the components which we know are 1 over x add 1 and 2 over x minus 1. If we did not know what these components were, we can still prepare the way by writing 3x add 1 all over x squared minus 1 equals 3x add 1 all over open brackets x add 1 close brackets open brackets x minus 1 close brackets equals blank over x add 1 plus blank over x minus 1, leaving blank the places for the numerators until we know what to put there. We always may assume the sign between the partial fractions to be plus, since, if it be minus, we shall simply find the corresponding numerator to be negative. Now, since the partial fractions are proper fractions, the numerators are mere numbers without x at all, and we can call them a, b, c, as we please. So in this case we have 3x add 1 all over x squared minus 1 equals a over x add 1 add b over x minus 1. If now we perform the addition of these two partial fractions, we get a open brackets x minus 1 close brackets add b open brackets x add 1 close brackets all over open brackets x add 1 close brackets open brackets x minus 1 close brackets, and this must be equal to 3x add 1 all over open brackets x plus 1 close brackets open brackets x minus 1 close brackets. And as the denominators in these two expressions are the same, the numerators must be equal, giving us 3x add 1 equals a open brackets x minus 1 close brackets add b open brackets x add 1 close brackets. Now this is an equation with two unknown quantities, and it would seem that we need another equation before we can solve them and find a and b. But there is another way out of this difficulty. The equation must be true for all values of x, therefore it must be true for such values of x as will cause x minus 1 and x plus 1 to become 0, that is, for x equals 1 and for x equals minus 1 respectively. If we make x equals 1, we get 4 equals a times 0 add b times 2, so that b equals 2. And if we make x equals minus 1, we get minus 2 equals a times minus 2 add b times 0, so that a equals 1. Replacing the a and b of the partial fractions by these new values, we find them to become 1 over x add 1 and 2 over x minus 1, and the thing is done. As a farther example, let us take the fraction 4x squared add 2x minus 14 all over x cubed add 3x squared minus x minus 3. The denominator becomes 0 when x is given the value 1, hence x minus 1 is a factor of it, and obviously then the other factor will be x squared add 4x add 3, and this again can be decomposed into open brackets x add 1 close brackets open brackets x add 3 close brackets. So we may write the fraction thus: 4x squared add 2x minus 14 all over x cubed add 3x squared minus x minus 3 equals a over x plus 1 add b over x minus 1 add c over x plus 3, making three partial factors. Proceeding as before, we find 4x squared add 2x minus 14 equals a open brackets x minus 1 close brackets open brackets x add 3 close brackets add b open brackets x add 1 close brackets open brackets x add 3 close brackets add c open brackets x add 1 close brackets open brackets x minus 1 close brackets. Now if we make x equals 1, we get minus 8 equals a times 0 add b open brackets 2 times 4 close brackets add c times 0, that is b equals minus 1. If x equals minus 1, we get minus 12 equals a open brackets minus 2 times 2 close brackets add b times 0 add c times 0, whence a equals 3. If x equals minus 3, we get 16 equals a times 0 add b times 0 add c open brackets minus 2 times minus 4 close brackets, whence c equals 2. So then the partial fractions are 3 over x plus 1 minus 1 over x minus 1 add 2 over x plus 3, which is far easier to differentiate with respect to x than the complicated expression from which it is derived. Case 2. If some of the factors of the denominator contain terms in x squared, and are not conveniently put into factors, then the corresponding numerator may contain a term in x as well as a simple number, and hence it becomes necessary to represent this unknown numerator not by the symbol a, but by ax add b, the rest of the calculation being made as before. Try, for instance, minus x squared minus 3 all over open brackets x squared add 1 close brackets open brackets x add 1 close brackets. Minus x squared minus 3 all over open brackets x squared add 1 close brackets open brackets x plus 1 close brackets equals ax add b all over x squared add 1 add c over x add 1. Minus x squared minus 3 equals open brackets ax add b close brackets open brackets x add 1 close brackets add c open brackets x squared add 1 close brackets. Putting x equals minus 1 we get minus 4 equals c times 2 and c equals minus 2. Hence x squared minus 3 equals open brackets ax add b close brackets open brackets x add 1 close brackets minus 2x squared minus 2 and x squared minus 1 equals ax open brackets x add 1 close brackets add b open brackets x add 1 close brackets. Putting x equals 0 we get minus 1 equals b. Hence x squared minus 1 equals ax open brackets x add 1 close brackets minus x minus 1 or x squared add x equals ax open brackets x add 1 close brackets and x add 1 equals a open brackets x add 1 close brackets so that a equals 1 and the partial fractions are x minus 1 all over x squared add 1 minus 2 over x plus 1. Take as another example the fraction x cubed minus 2 all over open brackets x squared add 1 close brackets open brackets x squared add 2 close brackets. We get x cubed minus 2 all over open brackets x squared add 1 close brackets open brackets x squared add 2 close brackets equals ax add b all over x squared add 1 add cx add d all over x squared plus 2 equals open brackets ax add b close brackets open brackets x squared add 2 close brackets add open brackets cx add d close brackets open brackets x squared plus 1 close brackets all over open brackets x squared add 1 close brackets open brackets x squared add 2 close brackets. In this case the determination of a, b, c, d is not so easy. It will be simpler to proceed as follows. Since the given fraction and the fraction found by adding the partial fractions are equal and have identical denominators, the numerators must be identically the same. In such a case, and for such algebraic expressions as those with which we are dealing here, the coefficients of the same powers of x are equal and of same sign. Hence, since x cubed minus 2 equals open brackets ax add b close brackets open brackets x squared add 2 close brackets add open brackets cx add d close brackets open brackets x squared add 1 close brackets equals open brackets a add c close brackets x cubed add open brackets b add d close brackets x squared add open brackets 2a add c close brackets x add 2b add d. We have 1 equals a add c, 0 equals b add d, the coefficient of x squared in the left expression being 0, 0 equals 2a add c, and minus 2 equals 2b add d. Here are four equations from which we readily obtain a equals minus 1, b equals minus 2, c equals 2, and d equals 0, so that the partial fractions are 2 open brackets x add 1 close brackets over x squared add 2 minus x add 2 all over x squared add 1. This method can always be used, but the method shown first will be found the quickest in the case of factors in x only. Case 3. When, among the factors of the denominator, there are some which are raised to some power, one must allow for the possible existence of partial fractions having for denominator the several powers of that factor up to the highest. For instance, in splitting the fraction 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets, we must allow for the possible existence of a denominator x add 1 as well as open brackets x add 1 close brackets squared and x minus 2. It may be thought, however, that since the numerator of the fraction the denominator of which is open brackets x add 1 close brackets squared may contain terms in x, we must allow for this in writing ax add b for its numerator, so that 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets equals ax add b all over open brackets x add 1 close brackets squared add c over x add 1 add d over x minus 2. If, however, we try to find a, b, c and d in this case, we fail because we get 4 unknowns and we only have 3 relations connecting them, yet 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets equals x minus 1 all over open brackets x add 1 close brackets squared add 1 over x add 1 add 1 over x minus 2. But if we write 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets equals a over open brackets x add 1 close brackets squared add b over x add 1 add c over x minus 2, we get 3x squared minus 2x add 1 equals a open brackets x minus 2 close brackets add b open brackets x add 1 close brackets open brackets x minus 2 close brackets add c open brackets x add 1 close brackets squared, which gives c equals 1 for x equals 2. Replacing c with its value, transposing, gathering like terms and dividing by x minus 2, we get minus 2x equals a add b open brackets x add 1 close brackets, which gives a equals minus 2 for x equals minus 1. Replacing a with its value, we get 2x equals minus 2 add b open brackets x add 1 close brackets, hence b equals 2, so that the partial fractions are 2 over x add 1 minus 2 over open brackets x add 1 close brackets squared add 1 over x minus 2, instead of 1 over x add 1 add x minus 1 all over open brackets x add 1 close brackets squared add 1 over x minus 2, stated above as being the fraction from which 3x squared minus 2x add 1 all over open brackets x add 1 close brackets squared open brackets x minus 2 close brackets was obtained. The mystery is cleared if we observe that x minus 1 all over open brackets x add 1 close brackets squared can itself be split into the two fractions 1 over x add 1 minus 2 over open brackets x add 1 close brackets squared, so that the three fractions given are really equivalent to 1 over x add 1 plus 1 over x add 1 minus 2 over open brackets x add 1 close brackets squared add 1 over x minus 2 equals 2 over x plus 1 minus 2 over open brackets x add 1 close brackets squared add 1 over x minus 2, which are the partial fractions obtained. We see that it is sufficient to allow for one numerical term in each numerator, and that we always get the ultimate partial fractions. When there is a power of a factor of x squared in the denominator, however, the corresponding numerators must be of the form ax add b, for example, 3x minus 1 all over open brackets 2x squared minus 1 close brackets squared open brackets x add 1 close brackets equals ax add b all over open brackets 2x squared minus 1 close brackets squared add cx add d all over 2x squared minus 1 add e over x add 1, which gives 3x minus 1 equals open brackets ax add b close brackets open brackets x add 1 close brackets add open brackets cx add d close brackets open brackets x add 1 close brackets open brackets 2x squared minus 1 close brackets add e open brackets 2x squared minus 1 close brackets squared. For x equals minus 1, this gives e equals minus 4. Replacing, transposing, collecting like terms, and dividing by x add 1, we get 16x cubed minus 16x squared add 3 equals 2cx cubed add 2dx squared add x open brackets a minus c close brackets add open brackets b minus d close brackets. Hence 2c equals 16 and c equals 8. 2d equals minus 16 and d equals minus 8. A minus c equals 0, or a minus 8 equals 0, and a equals 8. And finally, b minus d equals 3, or b equals minus 5. So that we obtain as the partial fractions 8x minus 5 all over open brackets 2x squared minus 1 close brackets squared add 8 open brackets x minus 1 close brackets over 2x squared minus 1 minus 4 over x add 1. It is useful to check the results obtained. The simplest way is to replace x by a single value, say plus 1, both in the given expression and in the partial fractions obtained. Whenever the denominator contains but a power of a single factor, a very quick method is as follows. Taking, for example, 4x add 1 all over open brackets x add 1 close brackets cubed, let x add 1 equal z, then x equals z minus 1. Replacing, we get 4 open brackets z minus 1 close brackets add 1 all over z cubed equals 4z minus 3 all over z cubed equals 4 over z squared minus 3 over z cubed. The partial fractions are, therefore, 4 over open brackets x add 1 close brackets squared minus 3 over open brackets x add 1 close brackets cubed. Application to differentiation. Let it be required to differentiate y equals 5 minus 4x all over 6x squared plus 7x minus 3. We have dy over dx equals minus open brackets 6x squared plus 7x minus 3 close brackets times 4 add open brackets 5 minus 4x close brackets open brackets 12x add 7 close brackets all over open brackets 6x squared add 7x minus 3 close brackets squared equals 24x squared minus 60x minus 23 all over open brackets 6x squared add 7x minus 3 close brackets squared. If we split the given expression into 1 over 3x minus 1 minus 2 over 2x add 3, we get, however, dy over dx equals minus 3 over open brackets 3x minus 1 close brackets squared add 4 over open brackets 2x add 3 close brackets squared, which is really the same result as above split into partial fractions, but the splitting, if done after differentiating, is more complicated, as will easily be seen. When we shall deal with the integration of such expressions, we shall find the splitting into partial fractions a precious auxiliary. End of section 24.